In this lesson, we want to talk about graphing sine and cosine. All right, so to start out the lesson, I'm going to talk about something called a periodic function. So when we think about sine and cosine, these guys are called a periodic function because their values repeat in a regular pattern. So to see what I mean by that, let's revisit the unit circle from the last section. So from our unit circle, what we see here is that as we travel around our unit circle, so in other words, if I start here, let's say I make a counterclockwise rotation, okay, so a positive angle measure, and I do one full rotation. Well, that's going to be an angle measure of 2 pi. We already know that, okay? But as I continue past 2 pi, so let's say I created an angle that was greater than that, so I keep going around, okay? So let's say I make an angle that's 4 pi, so 2 full rotations. What's happening is these values for sine and cosine are going to repeat themselves, okay? So anything past 2 pi. So when we talk about 2 pi for sine and cosine, this is going to be known as our period. It's the smallest possible positive value for where these function values, okay, these values for sine and cosine are going to repeat themselves, okay? Let's think about this with a simple little example. Let's say I think about this angle measure here, which is pi over 6, or 30 degrees. I know that the sine of pi over 6 is given by the y value of that point right there. Okay, so this is equal to 1/2, okay? But also, if I was to rotate around another 2 pi, okay, so another 2 pi, I'm going to get back to that same point right there, okay? So I have a coterminal angle, and my sine value is going to be the same. So in other words, if I said the sine of pi, let me use parentheses here, pi over 6 plus another full rotation would be 2 pi. Let's go ahead and write that as 12 pi over 6 so we can have a common denominator. This is going to be equal to 1/2 as well, okay? If I add these up, pi plus 12 pi is 13 pi. So this is 13 pi over 6, okay? This is 13 pi over 6. If you punch this into your calculator, you'll see that you get the same value either way. And you can keep going around another 2 pi, or you can go the other way. You can go clockwise 2 pi. So basically, as you're adding these multiples of 2 pi, you're getting these coterminal angles, and so your sine values are the same, and also your cosine values are the same. So if we go back up to our little definition of a periodic function, you see we have f of x. X is just some member of the domain. In the case of sine or cosine, it would be any real number. This is equal to f of, you have that same x value, plus n, which is some integer, times p, which is going to be our period, which in this case is going to be 2 pi, okay? So I could say something like the sine of x, and I could say really this is equal to the sine of, I'll say that same x value, plus some integer n, times the period p, which is 2 pi, okay? This is something that is very important to write down. We're going to use this not only in this section, but also when we solve trigonometric equations. So then we could say the cosine of x is equal to the cosine of, you have your same value for x, plus your n times your 2 pi, okay? In our example, we saw, let me write this off to the side, that the sine of basically the pi over 6 was equal to the sine of, we had pi over 6 again, okay? And then what we did was we added just 2 pi, right? Our n was 1. But really, you could put n times, let me scooch this down because it's going to run out of room, n times your 2 pi here, okay? So you can plug in anything for n as long as it's an integer, and this statement would be true. You would basically get 1/2 on the left and 1/2 on the right after you evaluate. Okay, before we move any further, I want to clear up something that is a common source of confusion, and that is what to do with this point right here, okay, which contains an x value and a y value when you're working with something like y equals the sine of x or y equals the cosine of x, which we're going to get to in a moment. Let me just erase this, okay, and we'll build up to what we need to do. Okay, let me actually erase this. I want to show you again where things come from, even though we talked about it in the last section. We have a unit circle here, okay, so that means the radius is 1. Okay, so this r value here, or this distance from right here to right here is 1. Okay, you can see that from here, which is the origin, 0, 0, to here, which is 1, 0, that's 1. From here to here is 1, from here to here is 1, from here to here is 1. So we see the radius is 1. Now, if I go back to my definition of cosine of theta and sine of theta, again, if I have a point on the terminal side, well then the cosine of theta is given as x over r, and the sine of theta is given as y over r. Well, here, my r value is 1, so the cosine of theta is exactly equal to x, or the x coordinate from that point. So this is exactly equal to x. For the sine of theta, again, y over r is 1, so this guy is exactly equal to the y coordinate from that point. So it's really important to understand that when I grab this x value, it's the cosine of theta. When I grab this y value, it's the sine of theta, okay? Now we move on, and we introduced this s now instead of theta. Okay, that further complicated things. The reason we're using this is so that we can have real numbers as our domains for the trigonometric functions, right? We started to call these guys circular functions. So s here is the arc length of the intercepted angle, okay? So s is exactly equal to theta, okay? So now we can say that for this point right here, the x value is the cosine of s, okay? This arc length here. And then the sine of s is going to be y. Okay, so that's all we really need to know. When we come back to our little unit circle, if we think about something like y is equal to the sine of x, or let's say y is equal to the cosine of x, it's important to know what's going on, what you're plugging in for x, and what you expect as an output for y. We are plugging in angle measures here, typically in radians, for x, and we are getting sine values out for y. Okay, so in other words, if I look at, let's say, this point right here, I am not taking this as the x value and this is the y value. That is not how that works. I want the angle, okay, so pi over 6. In other words, let me erase this for a moment. If I said y is equal to the sine of pi over 6, what's the y value? Well, the sine of pi over 6 is given by this y value here for this point, right? The y coordinate from that point, which is 1/2. So this guy right here would be 1/2. In other words, a point would be pi over 6, comma, 1/2. Another one would be, let's say I did pi over 4. Well, the sine value would be square root of 2 over 2. So another one would be pi over 4, comma, square root of 2 over 2. Okay, you can continue making points like this to sketch your graph of sine. I'm going to show you a better way in a moment, but for right now, I just want to make sure that's clear for you. Okay, if I did a few with cosine, just really quickly, so y equals the cosine of x. Again, if I plugged in pi over 6, so y equals cosine of pi over 6. Well, what is the cosine of pi over 6? I'm not looking at the y value now. I'm looking at the x value for this point. Okay, it's square root of 3 over 2. So this would be square root of 3 over 2. And so the ordered pair there would be pi over 6, comma, square root of 3 over 2. Okay, so it's very important that this is clear for you in terms of what you're plugging in for x and what your output is for y. Now, with that being said, let's go through and let's think about some of the basic points that you're going to get from a sine graph. Okay, so we're going to be looking at y equals the sine of x. This is a function, so you can use function notation. F of x equals sine of x. It's not a one-to-one function, but we'll talk about that later on in the course. Okay, so if we look at these y values here, we're going to be focused here, 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 and here, right? So as we start from an angle measure of 0, okay, and we go to pi over 6, pi over 4, pi over 3 to pi over 2, you'll see that the sine of x, or the y value, okay, is going to increase from 0 to 1/2, square root of 2 over 2, square root of 3 over 2 to 1, okay? Then as we go from pi over 2 to pi, this guy's going to now decrease from 1 down to 0, okay? So you're going to go to square root of 3 over 2 again, square root of 2 over 2, and then 1/2, and then back to 0, okay? Then as we get into our quadrant 3 and our quadrant 4, remember sine is going to be negative. So from pi down to 3 pi over 2, we're going to be decreasing from 0 down to -1, okay? So you can go to -1/2, negative square root of 2 over 2, and negative square root of 3 over 2. Finally, you get to -1. And then lastly, from 3 pi over 2 up to 2 pi, so up to 1 full rotation, we're going to increase from this -1 back to this 0, right? So you're going negative square root of 3 over 2, negative square root of 2 over 2, and then finally -1/2. Now, you do not need all of these values as ordered pairs. You can just start off by taking the first few guys that you get in the first quadrant, along with your quadrantal angles, okay? And that's basically enough to get started. After that, I'll show you that you really only need 5 key x values to draw this guy over one period. You're going to draw a wave-like function, okay? So if we start with 0, that's our angle measure, the y value is 0. Then pi over 6, you get 1/2. Then if we do pi over 4, you get square root of 2 over 2. Then if you do pi over 3, you're going to get square root of 3 over 2. Then if you do pi over 2, you get 1. Pi, you get 0. 3 pi over 2, you get -1. And 2 pi, which is 1 full rotation, you are back to 0. All right, so now that we have some basic points, let's go through and draw our first graph of, I'm going to go ahead and label this as f of x is equal to the sine of x. I'm specifically going to say here, because this is over one period, so from 0 to 2 pi, so one rotation, I'm going to say that x is greater than or equal to 0 and less than or equal to 2 pi. I'll show you in a minute that this continues to the right and to the left forever, okay? So what we've done here, we've put a little bit of detail into this, more detail than you really need. You'll see I have these notches that are going to be in increments of pi over 6. We're going to start out with an angle measure of 0, okay? Again, the sine of 0 is 0, so your x value is 0, your y value is 0, okay? Then as you get to pi over 6, what's going to happen is your sine of pi over 6 is a half. So you can say this right here is a half, okay? And you could label that, this is pi over 6, comma 1/2, and I'm trying to make that a little bit better here, okay? Then as you continue, then you have your pi over 3, and the sine value for that is going to be square root of 3 over 2. So this right here would be your pi over 3 and then square root of 3 over 2, okay? And then at pi over 2, you get to the maximum y value, which is 1, okay? So that's right there. Then you start decreasing again. Remember, after pi over 2, you're coming back down to a y value of 0, so you're decreasing. So now this is your maximum, then you're going to come back to your square root of 3 over 2 in terms of your y value. You're going to come back to your 1/2 in terms of your y value, and then you come back to 0 or an x-intercept when you get pi, okay? So then as we continue from pi to 3 pi over 2, we are decreasing from 0 down to -1, which is the minimum, okay, for the y value. Then as we go from 3 pi over 2 back to 2 pi, back to one full rotation, we're going back to 0. This just goes directly in line with what we were doing on the unit circle. Now, when you graph these guys, let me erase all of this. You really do not need all of this detail, okay? I put some notches here in terms of pi over 6. Typically, if you're asked to graph something over one period, you're going to make 5 notches for the 5 key x values, okay? You're going to have a starting point, you're going to have a quarter point. Let me mark these off. So you have a starting point, a quarter way point, a middle point, a 3/4 way point, and then an ending point, okay? For the basic sine graph, it's really easy because these key x values are going to be your quadrantal angles, right? So this is, if you think about it in degrees, if that's easy to remember, this is 0 degrees, 90 degrees, 180 degrees, 270 degrees, and then 360 degrees, okay? So very easy to get those 5 values. I'm going to talk about in a moment splitting up the period into fourths, but I'll get to that in a moment. So let's go down here, and I want to think about what happens when we extend this to the right and to the left. Well, again, if I start off here with my x value of 0, let me write this out. So now this is f of x equals sine of x. Okay, no restriction. We're going all the way through. One full rotation or one cycle would be, I would go up to 1, I would go back through my x-intercept, down to the minimum, and then back up to my x-intercept. Okay, so this is one cycle or one rotation on the unit circle. Every other part of that graph is just made up of repetitions of this. Okay, you can see this is called a sine wave. Okay, so when you graph this guy, you're going to have your 5 key points. So 1, 2, 3, 4, 5, given by the 5 x values, which I'll talk about in a moment, and then the corresponding y values, obviously. And then you're going to sketch that wave and just continue that wave indefinitely to the right and to the left based on what your teacher says. Okay, you've seen that I've marked this off in increments of 2 pi, so that's your period. And another way we want to think about this, if you're going this way, okay, think about what a negative angle measure means. This graph is in terms of pi over 2, right? Those are the notches. So this is negative pi over 2. This is negative pi. This is negative 3 pi over 2. Remember what it means to have a negative angle. It means I'm rotating clockwise. If I go back to the unit circle, if I start here and I rotate this way, okay, I'm going to end up with negative pi over 2, which is coterminal with 3 pi over 2. So the sine value is negative 1. Then as I keep going, I'm going to end up with a negative pi. The sine value is 0, right? This is coterminal with pi. Then as I go and I continue, then I'm going to end up with negative 3 pi over 2. This is coterminal with pi over 2. So the sine value here is going to be 1. And then finally, as I make my full rotation going clockwise now, okay, I'm going to end up with negative 2 pi, and my sine value there is going to be 0 once again. So when you return, if you think about this, again, as we get to an x value of negative pi over 2, our y value is going to be negative 1. As we get to an x value of negative pi, our y value is going to be 0. As we get to an x value of negative 3 pi over 2, our y value is going to be 1. As we get to an x value of negative 2 pi, a full rotation, we're right back to 0. We're hitting the x-intercept. Now, here are a few things that you absolutely need to know when you work with the sine function. First off, this guy is continuous across its entire domain. The domain is a set of real numbers, okay? So that means you can plug in any real number you want, and you'll get a corresponding y value. It also means that when I say continuous, you can graph this guy without ever lifting your pencil. There's no holes, no gaps, nothing like that, okay? Additionally, when we think about the x-intercepts, so you think about here and here and here and here and here and here and here, these are of the form, let me write this out, the x-intercepts are of the form n times pi, okay? Where n is some integer. So you can think about this as being 0 times pi, that's 0, then 1 times pi is pi, then you'd have 2 pi, then 3 pi, then 4 pi, work going negative, so you'd have basically negative pi and negative 2 pi, so on and so forth. Now your range for sine and also for cosine is from negative 1 to positive 1. So the minimum y value would be negative 1, and that's included, and the maximum y value is positive 1, and that's included. So we can say our range, and let me put the e there, forgot that. So our range is going to be from negative 1 to positive 1, like that. Now, the last thing I want to talk about is that this graph is symmetric with respect to the origin. So when this happens, we call this an odd function. So let me go back to the unit circle, and let me demonstrate this real quick. For an odd function, f of negative x is equal to the negative of f of x. Now, this is going to come up in our section on identities. We're going to need this, what we call negative angle identity, to rewrite things. But for right now, I just want you to understand this concept. If I have the sine of negative x, let me put this in parentheses, this is equal to the negative of the sine of x, okay? Let's just go back to this pi over 6. If I do the sine of, let's say, negative pi over 6, what would that be? Well, that would be me starting here and rotating clockwise, okay, to right there. It's coterminal with 11 pi over 6, so the y value for that point would be negative 1/2. So this is negative 1/2, let me write that. This is equal to the negative of the sine of x, okay? I have a negative x, I want just x, so the negative of the sine of pi over 6. So the sine of pi over 6 is given by this y value here. So this is going to be the negative of sine of pi over 6, which is going to be negative 1/2 as well. Okay, let's move on now and talk about graphing variations of the sine graph. I'm going to go through all the different transformations that you're going to come across. We're going to start off with the vertical stretch or vertical compression, okay? And in order to graph these variations by hand, what you want to have are the x-intercepts. You want to have your maximum point and then your minimum point, okay, if you're looking at one period, okay? So when we look at one period or one cycle, you think about your x-intercepts for your basic sine graph. Let me write this out again. So f of x is equal to the sine of x, or x is greater than or equal to 0 and less than or equal to 2 pi. Your x-intercepts occur at the beginning, the middle, and the end of your period, okay? So 0, pi, 2 pi, okay? Then in terms of your maximum and your maximum is going to occur at a quarter way through the period, okay? So 2 pi divided by 4, or 2 pi times a fourth, that's going to give you pi over 2. And then your minimum is going to occur at 3/4 way through your period. So 3/4 times 2 pi will give you your 3 pi over 2, okay? So what you want to do to get these x values in any situation is you want to set yourself up a little table, okay? Or you could say just some scratch work. And you want to first divide your period by 4, okay? So with the basic sine function, the period is 2 pi, okay? We're going to divide this by 4. So we cancel this with this and get a 2. So basically you have your pi over 2, okay? So you're going to start off where your cycle begins. For the basic sine function, it's going to start at 0, okay? So let me put 0 here. And then what you're going to do is you're going to just keep adding pi over 2 to the previous value. So here, x sub 2, or the second x value, is this x sub 1, which is 0, plus your pi over 2, so that's pi over 2, okay? And then here it's pi over 2 plus pi over 2, which is pi, and then plus pi over 2 again, which is going to be 3 pi over 2, and then plus pi over 2 again, which is going to give me back to 2 pi, okay? Typically, as a check, a lot of books will say take your ending value minus your beginning value, so 2 pi minus 0. If that equals your period, you're pretty much good to go. Okay. Now, that doesn't mean you didn't make some mistake in between, but at least you know that your cycle is the right length. All right, so let's start talking about some of the function transformations that we're going to see. The first type is very, very easy. This is where we have a vertical stretch or a vertical compression. You'll recall from earlier in the course, if we have something like a multiplied by f of x, basically if this a value, we'll say the absolute value of that, if that's greater than 1, you're going to have a vertical stretch. If you have the absolute value of a being greater than 0 and less than 1, now you're going to have a vertical compression, okay? So all your function values or your y values are being multiplied by this guy a here, okay? So what we see here is we have f of x is equal to a, that's multiplying the sine of x. So the original function is sine of x, a is now multiplying that, and I'm specifically going to say that a is any real number that is not 0, okay? So some non-zero real number. So the example we start with is f of x equals 2 times the sine of x. So basically we know that since this is a 2, and the absolute value of 2 is 2, and that's greater than 1, this would be a vertical stretch, right? Because all the function values, all the y values are being multiplied by 2 when we compare it to the original function, f of x equals sine of x. And you can see this. So the x-intercepts here, here, and here, obviously the y values are 0, so those are going to stay the same because 0 times 2 is still 0. But if you look at this maximum y value of 1, okay, if you multiply that by 2, you're now at 2. Okay, 1 times 2 is 2. If you look at the minimum y value, which is negative 1, you multiply that by 2, you're down here to negative 2. Okay, so this guy has been vertically stretched by a factor of 2. Now, when we think about the period for a function of this form, it's still going to be 2 pi. Okay, so we haven't introduced any type of shift. We haven't introduced any type of horizontal stretch or compression. So the period is still 2 pi. We're still starting out with an x value of 0. So you still have the same 5 key x values at 0, pi over 2, pi, 3 pi over 2, and 2 pi. Okay, so basically to get these points, you really just need to think about the fact that you're multiplying the y values from your original function by 2. Okay, that's all you really need to do. Now I'm going to talk about in a moment the fact that you can use this a value to find your maximum and minimum y value, but we're going to talk about that later on when we talk about the amplitude. Okay, let's look at another example. Again, I'm working with f of x is equal to a times the sine of x. Here we have f of x equals 1/2 times the sine of x. So what do you think is going to happen here? We're going to have a vertical compression. Okay, so basically all your y values now are multiplied by 1/2, and that's compressing your graph, okay? So again, you get your x values in the same way. The period has not changed, so it's still going to be 0, pi over 2, pi, 3 pi over 2, and 2 pi. That part's really easy. So the x-intercepts, the y values are always going to be 0. And then for these y values here on your new graph, again, you can just multiply the previous ones by 1/2, or you can evaluate the function there. Or again, I'll talk in a moment about how to get the minimum and maximum value. You might notice that when we had 2 times the sine of x, it was 2 and negative 2. When we just had sine of x, it was 1 and negative 1. Here we have 1/2 times the sine of x, and it's basically 1/2. I can put that in. This is 1/2. And then down here, this is negative 1/2. So you see the pattern is that your maximum and minimum is related to this right here. We'll talk more about that in a moment. All right, let's take a look at one more of these in this form. So now we're going to look at f of x equals negative 2 times the sine of x. So you actually have two different things going on. One, you have a vertical stretch of a factor of 2. And then you have that negative there that's going to cause a reflection across the x-axis. So compared with the graph of f of x equals the sine of x, basically all your y values are multiplied by negative 2. Okay, so again, you have the same period, so you have the same x-intercepts. So you're going to have this guy, and this guy. Those are going to be the same, right? Y values are still going to be 0. But when you look at this guy and this guy, okay, you can go from your basic sine graph and you can just multiply those y values by negative 2. So 1 multiplied by negative 2 gives you this negative 2. And then negative 1 multiplied by negative 2 is going to give you this positive 2, okay? And if you think about this in terms of your f of x equals 2 times the sine of x, again, the negative there, if you have the negative of f of x, whatever you're working with, it's a reflection across the x-axis. So if we go back and look at this guy one more time, you can see that we have this peak here, okay, where your x value is pi over 2 and your y value is 2, okay? So this is going to be reflected across the x-axis. And so now this is going to be your minimum point, right? So at pi over 2, comma, negative 2. And this guy right here, which was your minimum, right, where you had 3 pi over 2, comma, negative 2, well, now this is going to come up and be your maximum. It's getting reflected across the x-axis. So now it would be 3 pi over 2, comma, positive 2. If we go back, you'll see that's exactly what we have here. Okay, so let's make a few generalizations. You should notice that this is negative 2 here, and the maximum is still 2, and the minimum is still negative 2. So what I would say here is that if you have this f of x is equal to a times the sine of x, where, again, we're going to say a is not 0, but it could be any real number you want other than that, then basically, if you think about the range, okay, and this is going to give us our maximum y and our minimum y, then what I do, I'll put some brackets here, and I'll say it's from the negative of the absolute value of a to the absolute value of a. And I'm using these square brackets here because these values are included, right? If we look at this negative 2 here, the absolute value of that is 2, so you'd want negative 2 to positive 2. Again, both are included. If you went back to a half, it would be negative a half to positive a half. Both are included. If you had positive 2, again, it would be negative 2 to positive 2. Both are included. If this was 57, then it would be negative 57 to positive 57, so on and so forth. All right. The next concept I want to talk about is known as the amplitude. This is something you need to know when you work with the sine or cosine function. And it's going to be the same for the basic sine graph and also the cosine graph, which we'll talk about later on. So over one period, let me write this out. So f of x equals the sine of x. Again, x is greater than or equal to 0 and less than or equal to 2 pi. So we're looking at this right now. And basically, you'll see that I've written that the amplitude is 1. So what does that mean and where does it come from? Well, basically, when you think about the amplitude, you're thinking about something that describes the height of the graph both above and below your horizontal line that passes through the middle of the graph. So for the basic sine or cosine function, that's going to be your x-axis, okay? That's going to be your x-axis. So it would be the line y equals 0, okay? So from this guy right here to this guy right here, your minimum y value is negative 1. It's a distance of 1. Or you could say from right here to up here, that's a distance of 1 as well, however you want to draw it. Now, the formula we use is basically to grab the a value and take the absolute value of that, and that's going to be your amplitude. Here, you can think about your a value being 1, okay? So the absolute value of 1 is 1, so the amplitude is 1. A more precise definition comes from the fact that you're taking half of the difference between the maximum and minimum values. So if you take your maximum, which is 1, you subtract away your minimum, which is negative 1, minus a negative is plus a positive, so this becomes 1 plus 1, which is 2. If you took half of that, you're right back to 1. If you want to look at another example of this, again, we've been working with f of x equals 2 times the sine of x. Again, just take this number out in front, which in this case is a 2. Take the absolute value of it. So if it was 2 or negative 2, the amplitude is just going to be that number. And again, you can see the distance from this guy right here down to your minimum, okay, that's going to be a distance of 2 units. And again, you could just go 2 minus a negative 2. That's going to be positive 4. You half that and you're back to 2, okay? If you wanted a more generic formula, again, you can go f of x equals a times the sine of x, where a is not 0. And you could say, okay, well, I know the range from earlier is from the negative of the absolute value of a to the absolute value of a, okay? So that tells me that the minimum y value would be the negative of the absolute value of a. So let's just go ahead and say the maximum y value is going to be the absolute value of a. So a minus a negative a is going to be 2a, okay? So this is 2a, and if I half that, I just get a. And of course, we're going to use absolute value bars just to account for the fact that this guy could be positive, it could be negative. So we want to account for that, so we use absolute value bars. So your amplitude, I'm just going to put AMP, is always found as the absolute value of a, this guy out in front. All right, what I want to do is consider when the period for sine or cosine is not 2 pi. I'm going to work with the sine function, but this works the same for the cosine function. So we have something like f of x equals a times the sine of, now we have bx, and I'm specifically going to work with b being greater than 0 in our examples today. You might get examples where b is less than 0. I'll talk about how to deal with that, but we're not going to get to that scenario until the next chapter, okay? So I'm going to put a comma here. I'm also going to say that a is not equal to 0, so any real number that's not 0. So in order to consider how this is going to change our graph and how this is going to change our period, I want you to first consider that if b is 1, that's what we've been working with. So f of x is equal to a multiplied by the sine of x. This has a default period. So this has a default period of 2 pi, okay? Now, where does that come from? Well, it comes from the fact that as you rotate on your unit circle, starting at an angle measure of 0 in terms of radians, around one rotation going counterclockwise, to complete that rotation, you end up with an angle measure of 2 pi, okay? So that's one cycle. So we would say x is going to be greater than or equal to 0 and less than or equal to 2 pi, okay? So this is what happens as long as you have this format. It does not matter what the value for a is. Remember, this is affecting us with a vertical stretch or vertical compression. This could be negative, it could be positive, it could be a fraction. It doesn't matter. It will not change your period. Now, when you consider that you're throwing this b into the mix, now something is multiplying x, okay? So it's changing the speed at which you're going through one cycle, okay? So you can throw this into your inequality, okay? And you can basically say that I'm going to put a bx inside of here because my function is going to complete one cycle as bx now increases from 0 to 2 pi. So this might give you a horizontal stretch or horizontal compression. Okay, it's going to change the speed at which you complete one cycle. And basically, to figure out what your period is, you're just going to divide everything here by b. Okay, you're going to solve this for x. 0 divided by b, well, we know that b is not 0, so this would be 0. Okay, so let me write 0 here. This is less than or equal to, well, the b's would just cancel out. B divided by b is 1, so this is just x. And then this is less than or equal to your 2 pi over b. Okay, so we don't have any horizontal or vertical shifts going on. Your starting point for the cycle, okay, would still be 0 for the x value. And now your ending point for the cycle would be 2 pi over b. Okay, so we'll update the period and just put 2 pi over b. Okay, like that. And this is what you want to use as a general formula. Okay, let me get rid of this. And I want to talk about some other things. First and foremost, if you are in this section in your textbook and they are giving you problems where b is negative, you can just use the absolute value bars for right now. When we get to the next section, I'll show you how to rewrite this based on the fact that sine is an odd function and cosine is an even function to where b is always greater than 0. Okay, but for right now, you can use the absolute value bars to get your period. Now, what I said earlier was that this would create a horizontal stretch or a horizontal compression. Now, where is that coming from? Let's think about a few basic examples. Let's say I said I had something like f of x is equal to, forget about the a, we'll just keep that as 1 each time. I'll say the sine of 2x. Well, let's first think about the period. So the period, okay, would be what? Well, I would have 2 pi over my b value. This is my b value, it's the coefficient of x. So 2 pi over 2, well, these are going to divide out, it's just pi. So if I think about this, it's completing a cycle, okay, starting with an x value of 0 and ending with an x value of pi, versus normally starting with an x value of 0 and ending with an x value of 2 pi. So it basically did it in half the time, right? So this is going to compress our graph horizontally, okay? So basically you can think about the fact that if your b is greater than 1, it is increasing the speed at which this bx here is going from 0 to 2 pi, okay? So obviously that is giving me a horizontal compression by a factor of 1 over b, okay? So this is horizontally compressed by a factor of 1 over b. Let me erase this and let's talk about the next situation. So if this was a value between 0 and 1, so a fractional value, now it's slowing it down, okay? So I'm going to be horizontally stretched. So let's say we looked at something like f of x is equal to, let's just do, I'm going to keep my a value as 1, so I'll do sine of 1/2 times x. Well, basically this is going to stretch me out, okay, by a factor of 1 over, you would take this 1/2 here, okay, so you're going to flip this, and this is going to be 2. Okay, so it's going to stretch me out by a factor of 2. Again, to think about this with the period, your period is always going to be, and I probably didn't write that correctly, so let me put this back in here. So the period would be 2 pi over b. Now, if I'm dividing by a half, I might as well just multiply by 2. So this is just going to be 4 pi, okay? So before, it went from 0 to 2 pi. Now it's going from 0 to 4 pi. So that is stretching the graph horizontally, right? It's taking twice as long. So let's look at a simple little diagram here. I think this will make a little bit of sense for you. So we have f of x equals a times the sine of bx. Again, we don't have any vertical or horizontal shifts, so the starting x value for your cycle is going to be at 0, and then you would add quarter periods, okay, to get these other notches. So you have your 2 pi over b, you'd multiply by a fourth to get your quarter periods, so you can cancel this with this, okay, and basically it's going to be pi over 2b, okay, that's what you're going to be adding each time. So plus pi over 2b, plus pi over 2b, plus pi over 2b, plus pi over 2b. You're still going to have your same 3 x-intercepts, okay? And essentially, you're going to have your maximum and your minimum, and you can get those from your amplitude, which is the absolute value of a right there, okay? Your maximum is going to occur at the absolute value of that guy, and then the minimum is going to occur at the negative of the absolute value of that guy. All right, let's look at 2 examples here real quick. I'll give you one where there's a horizontal compression, and then I'll give you one where there's a horizontal stretch. So we have f of x equals 3 times the sine of 2x. So the first thing I'd like to do if you're going to graph this, find your amplitude, okay? This is going to help you to figure out what's the maximum and the minimum. So this guy, again, if this is 3, it's always the absolute value of that number, so it's going to be 3, okay? Then find your period. So what is the period here? It's 2 pi over b. In this case, your b value is 2, so 2 pi over 2. So this is just going to be pi, okay? So we know because this guy right here, this 2 is greater than 1, we're going to have a horizontal compression by a factor of 1 over that number, so by a factor of 1/2. And you can see our starting x value is 0, our ending value is pi, so this is being completed in terms of one cycle in half the time, okay? So once you have those two things, you're going to go through and add these quarter periods. Let me erase this real quick and just put pi here, okay? So a quarter period would be this guy divided by 4, so it's pi over 4, okay? So we don't have any shifts yet, so we're starting with an x value of 0, then you add pi over 4, 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 right? So really easy. And you can see that pi minus 0, okay, gets you back to pi, which is your period. That's always something you check. I know it's not that important here, but when you get into things like a phase shift, which we'll talk about here shortly, it's going to be important to do that, okay? So you have pi over 4, you have pi over 2, 3 pi over 4, and then pi, okay? So you know that at the beginning, the middle, and the end, you have your x-intercepts. So the y value is already figured out for you. It's going to be 0. When you get to a quarter of the way through, and you get to 3/4 of the way through, you know that you're going to be at your maximum for a quarter of the way through, and your minimum for 3/4 of the way through. And again, from your amplitude, you know that's 3. So the maximum's at 3. Okay, that's your y value. And your minimum is at -3. Okay, so that's enough to get you the 5 key points for this sine graph here. And then just connect the points with a smooth sine wave. That's all you need to do. All right, let's look at an example now where we're going to have a horizontal stretch. So we're going to have f of x equals 3 times the sine of x over 3. And you might want to rewrite this. I'm going to go f of x is equal to, I'll put my 3 times my sine of, let me make that sign a little bit better. My sine of, instead of x over 3, I'm going to put 1/3 being multiplied by x like this. That way it's crystal clear that the b value here is 1/3. Okay, so let's start off by thinking about our amplitude. So I'm going to put AMP for amplitude. Obviously, it's just the absolute value of this number. So again, it's just going to be 3. Okay, so that tells me the maximum and the minimum, it's going to be 3 and -3, right? 3 for the maximum y value, and then -3 for the minimum y value, okay? Now, when we think about our period here, so when we think about our period, we're going to have 2 pi over this b. So 2 pi divided by 1/3. Basically, you're going to flip that fraction, okay? And you're going to have 3 over 1, and you're going to multiply that by 2 pi. So the period here is going to be 6 pi, okay? So now if we think about one cycle, now starting from this x value of 0 out to this x value of 6 pi. So that's going to be one cycle for us. And essentially, we can see that it takes longer to go through this cycle, right? Instead of 0 to 2 pi, now it's 0 to 6 pi. So what's happening is this is going to be a horizontal stretch of the graph, okay? By a factor, it's always by a factor of 1 over b. Here, b is 1/3, so 1 over 1/3 is equal to 3, okay? So horizontally stretched by a factor of 3. Now, when we talk about sketching the graph of this guy, really all you need to do is get your key x values, okay? So you know this first one is going to be at 0, and you know the y value there is going to be 0. So this is 0, 0. That's pretty easy to get. From there, you want to add quarter periods, right? So you're going to go 6 pi over 4. If I divide 6 by 2, I get 3. So let me write this as a 3. If I divide 4 by 2, I get 2. So 3 pi over 2 is what I'm adding each time. So basically this notch right here would be an x value of 3 pi over 2. So this point up here would be 3 pi over 2. And then I'm going to be at the maximum, which is 3, okay? So always when this guy is positive, I don't have any kind of reflection or anything like that, where we saw earlier we would reflect across the x-axis if this was a negative 3. I know that a quarter way through, I'm going to be at the maximum, okay, because this is positive 3. Now, halfway through, right here, I'm going to be back to my x-intercept. So to get that, I'm just going to add another 3 pi over 2 to my 3 pi over 2. That would give me 3 pi, right? So this point right here would be 3 pi, comma, 0. Okay, it's another x-intercept. Then I'm going to add another 3 pi over 2 to this. So that's going to give me 9 pi over 2. Okay, so that's going to be my guy right here. So this point right here would be 9 pi over 2. And then comma, you're going to be at your minimum. Here, that would be negative 3. So again, as long as this is positive here, your minimum is going to occur 3/4 of the way through. Okay, again, if you get a negative here, you got to reflect across the x-axis. So you got to keep that in mind. Okay, for right now, this guy is positive, so it's pretty easy. Then you add another 3 pi over 2 to this 9 pi over 2. And you're going to get your final x value of 6 pi. And of course, this is another x-intercept. So this is 6 pi, comma, 0. Okay, so once you get these 5 key points, this is enough to sketch one period of any sine function. So again, you're just going to connect the points with a smooth sine wave. All right, so we have 2 transformations left that we want to talk about. One is going to be a horizontal shift, so either shifting to the left or the right. When we talk about this with the circular functions like sine or cosine, this is called a phase shift. We also want to talk about a vertical shift, so shifting up or down. That's a lot easier to deal with, so we'll deal with that in a moment, okay? So right now we're going to look at f of x equals the a times the sine of. You're going to have this bx minus c inside of parentheses. And for right now, we're going to work with examples where b is greater than 0, just to keep things simple. Again, as we get into the next chapter, I'll talk about what to do when b is less than 0. And also what I'm going to do here is I'm going to say that a is not equal to 0. That should be obvious, but I want to list that as a restriction just so it's clear, okay? Now, when we talk about the phase shift, I want to first go back to something we learned a long time ago, just to jog your memory. So you know if you have something like f of x is equal to, let's say, the square root of x, and you compare that to g of x, which is equal to the square root of, let's go x minus 2, let's go h of x, let's say this is the square root of x plus 2, okay? Remember, when things are happening inside the function, it's a little bit counterintuitive, right? When you see x values, you're thinking horizontal axis, so I'm moving left or right. When you see this minus 2, most people assume that means that you have a shift based on this original graph, f of x equals square root of x, that you're going to go 2 units to the left. But in fact, it's the opposite. This guy is going to shift, this would shift 2 units to the right, okay? Now, what causes that? Well, you have to think about the fact that to undo what's being done to x, we've got to add 2. Right? That gets me back to where I was. In other words, one ordered pair, let's say 0, 0 that's on this guy, to get the same y value for this guy, the x value has to be 2 units larger. So it would have to be 2, 0. Okay? If you wanted to do another one, let's say you did for this guy, something like 9, 3. Okay? For this guy, again, the x value has to be 2 units larger. So now it would have to be 11, 3. Okay, because you've got to go 11 minus 2 to get to 9, and then square root of 9 would get you that 3. Here it's just square root of 9, which is 3. If you look at this guy, again, what's being done? I'm adding 2. So to undo that, I've got to subtract 2. So that means I'm shifting 2 units to the left. So I'm going to, let me change my marker here. I'm going to shift 2 units left. Okay, so you got to keep that straight in your mind. It's the opposite of what you think, right? You got to undo what's being done to x. Now, let me erase this. And what I'm going to do is I'm going to write this in a different way, okay? So I'm going to write f of x is equal to a times the sine of, I'm going to factor this b out. Now you might be saying, well, there's no b over here, so how are you going to do that? All you need to do if you want to factor that out is basically divide each term by b. So in other words, I can put a b out here, and then inside the parentheses, I can go ahead and say, well, bx divided by b is x, and then minus the c divided by b would be c over b, okay? So this is going to make your shift a lot more clear. You can do it from this form if you want. Most people do, But I advise if you're having trouble with this to write it like this. I can also say that A is not equal to 0, and I can say that B is greater than 0 for our examples. And you might want to make this crystal clear and put some brackets here. They're not needed, but that makes it a little bit cleaner, okay? So if I look at it in this form, I know that if C is positive and B is positive, that basically I'm subtracting away a positive number, okay? And I'm going to be shifting to the right by C over B units, okay? It's very, very simple. If, for example, this was a negative C, I know B is positive because I've made it that way, well, then you have minus a negative, which is plus a positive, right? So I could really write this as plus C over B. In this case, I'm going to shift to the left, okay, by C over B units. Or you could say, really to make that crystal clear, since I said that C was negative, by the absolute value of C over B units, okay, to make that crystal clear. Let's put this back to this original form. Now, if you want to work with it in this form, it's really the same thing, okay? All you would do is start off with bx minus c, and you could set that equal to 0, and you could say, well, how do I undo what's being done to x? Well, what I could do is I could add c to both sides, okay? Cancel that, and say I have bx is equal to c, divide both sides by b, and I'll say I have x is equal to c over b. So that's going to be your phase shift, okay? Again, dealing with whether it's going left or right is just based on the sign that you have. If b, again, is restricted to be positive, well, then if c is positive and you have it in this form, you're going to be shifting to the right by c over b units, okay? If c is negative, meaning you have plus a positive, you're going to go to the left by the absolute value of c over b units, okay? This one's a little bit tricky when you think about the signs when you're in this generic form. So let's go ahead and look at an example. I think it'll be a little bit clearer. Okay, so let's look at this f of x equals 4 times the sine of, we have the 2x minus 2 pi over 3. So if you wanted to, you could rewrite this. I'll go f of x is equal to, you'll go 4 times the sine of, I would factor out the 2, okay, and I would put that out in front. And then inside, you're going to divide everything by 2. So if I divide 2x by 2, I get x, and then minus. If I divide 2 pi over 3 by 2, it's like multiplying by a half. Basically, you would cancel that 2 out with the 2 in the denominator. So you would have your pi over 3, okay? So really, when you look at it, you can just go back to my simple example with the square root. You have this minus pi over 3. So your phase shift is just going to be pi over 3 units to the right, okay? If this was a plus here, I would be going pi over 3 units to the left, okay? That's how I would write it. It's the simplest way to do it. If you don't want to go through all this trouble of factoring it, you can always say that I want to do my phase shift as c over b, okay? So my c is going to be 2 pi over 3. Let me write this out. So my c is 2 pi over 3. And then divided by b. So I'm dividing by 2, okay? So that's like multiplying by a half. And again, this 2 would cancel with this 2, and you end up with pi over 3. And again, because this was positive here, what that means is that we're going to be shifting to the right by pi over 3 units, okay? So let me write out here that my phase shift is pi over 3, and this is to the right. So pi over 3, you can put units if you want, and you will put right, okay? So you can see that by looking at the graph. Normally we start at 0, 0. Now we've been shifted pi over 3 units to the right. So the first guy for this cycle to start it off, the x value is pi over 3, and the y value is 0. So pi over 3, comma, 0, okay? Now when we talk about the other 5 key x values, from this point, it's the exact same procedure, okay? Same song and dance. So I'm going to find my amplitude. Again, that's super easy to do. Absolute value of this number out in front. So the absolute value of 4 is 4, okay? And this is not a negative, it's a positive. So you know your maximum is going to occur at the quarter way through the period. Your minimum is going to occur at 3/4 of the way through the period. So we'll get to that in a moment. But you know basically the y value here would be 4. Let me go ahead and write it out. And the y value here would be negative 4, okay? So that's pretty easy. You also know that your y value at all your intercepts, okay, which is going to occur at the halfway point and at the ending point, is going to be 0. So that's pretty easy too. So let me go ahead and put those in. Now, how do we get these x values? How do I get this one, and this one, and this one, and this one? Again, you're just going to add quarter periods. So we first need to find the period to do that. So let's go ahead and find the period. And basically, if we look at it, we have a b value of 2. So we have 2 pi over 2, which is just going to be pi, okay? So if you wanted quarter periods, it's pi over 4. So I'm going to add increments of pi over 4, okay? And you can see I already have this listed. This is something you would have to do with either a calculator or by hand. So basically pi over 3 plus pi over 4 is going to give me this 7 pi over 12. So this is 7 pi over 12. Add pi over 4 again, and I'm going to get this 5 pi over 6. So 5 pi over 6. Add pi over 4 again, I'm going to get this 13 pi over 12. So let me write that in there. So this is going to be 13 pi over 12. And then add pi over 4 one more time, and I'm going to get to 4 pi over 3. So 4 pi over 3. Now, I talked about this earlier, and it might have not made sense at the time, but when you have a phase shift, you want to take this guy and this guy, and you want to do a little subtraction to make sure it equals the period. That way you know you didn't mess up when you were adding quarter periods, okay? So 4 pi over 3 minus pi over 3 does give me the period of pi, so I know I'm good to go, right? I have all my points, and then I can just sketch my graph by making a smooth sine wave through those points. Now, if you wanted to think about all the transformations that have occurred, some teachers will ask you for that. Basically, you can think about, okay, it's been vertically stretched by a factor of 4. It's been horizontally compressed by a factor of a half, right? So remember, it's 1 over b. Your b value here is 2, so 1 over 2 or a half, okay? This guy is basically running through a cycle in half the time. Your phase shift is going to be pi over 3 units to the right. All right, let's talk about the last graphing transformation, which is basically where we're going to shift up or down, okay? So a vertical shift. We have something like f of x equals a times the sine of bx minus c, and then plus d now. We're still going to say b is greater than 0. Again, we're going to deal with b less than 0 in the next chapter. And I'm going to specifically state that a is not allowed to be 0. This is just for clarity, okay? So here, because of this plus d, this is a vertical shift. You're going to go up by d units if d is positive. You're going to go down by the absolute value of d units if d is negative. Let's go ahead and look at an example. We have f of x equals 4. Let me write this out here. So f of x equals 4. Then multiplied by the sine of, you're going to have this 3x plus 3 pi over 4. I'm going to factor that 3 out. So inside, instead of 3x, I'm going to divide by 3. I'm going to have x, then plus. Instead of 3 pi over 4, let me write this out so nobody gets lost. I'm going to divide by 3, so that's like multiplying by a third. So you're going to see that the 3's are going to cancel, and you're going to have pi over 4 right here. Let's write that in. Close that down, okay? Let me scooch this over so everything fits. You also have this minus 1 here, so we'll put that out there. If you were to think about this, let me make that a little bit cleaner. If you were to think about this in terms of all the things that have been done based on the original sine graph that we were working with, well, you have a vertical stretch by a factor of 4, okay? You have a horizontal compression by a factor of 1/3. So 1 over b, in this case b is 3. You have a phase shift left by pi over 4 units because you have x plus pi over 4 inside here, okay? So you're going left by pi over 4 units, and then you're going down by 1 unit. That's what that negative 1 is going to do, okay? So if we think about this, we can get our amplitude. Again, we know that that is going to come from this number right here. The absolute value of 4 is 4. And normally, if we don't have a vertical shift, that's going to tell us the maximum and the minimum, right? So we would know it would be 4 and negative 4. So the range here is going to change because of this minus 1. Instead of 4 and negative 4, what you're going to have is everything shifted down by a unit. So now, instead of 4 for the maximum y value, you're going to have 3. Instead of negative 4 for the minimum y value, you're going to have negative 5. So your range is going to be from negative 5 to positive 3. Okay, so keep that in mind. Now, when you talk about your period, okay, your period, that's going to be 2 pi over b, and b is just 3, so that's pretty easy. And then you're also going to need the quarter periods, so 2 pi over 3 times a fourth. Let's go ahead and cancel this 2 with this 4 and get a 2. So your quarter periods here are going to be pi over 6. So I'm going to put quarter period is just going to be pi over 6, okay? So let's talk about how we can get this graph if you're trying to do this quickly. Remember, you start off with 0, 0 on the basic sine graph. So think about all the things that are going to be done to this guy. You're going to have a phase shift of pi over 4 units to the left. So that's going to take me this way by pi over 4 units. So that point would be here now. And then we're shifting down by 1 unit. So that point's going to be right there. Okay. So I got moved from 0, 0 to that point, which is going to be negative pi over 4, comma, the y value, instead of it being 0, right? Normally that's the x-intercept. It's been shifted down by a unit. So this is going to be negative 1. okay? Now, as we go to the next x value, so you've got this one, which is at the quarter, this one, which is at the half, this one at the 3/4, and this one at the full period, we're just adding quarter periods, right? So we're adding pi over 6 to get to the next x value, okay? So when I add pi over 6 to negative pi over 4, I'm going to get negative pi over 12, okay? So this is negative pi over 12. How do I get my y value? Again, this is positive here, so I know at a quarter way through I'm at the maximum, and the maximum is going to be 3. Okay, so pretty easy there. Then as I go back, this would have been an x-intercept, right? But it's not. It's been shifted down by 1 unit, so I know the y value here is going to be negative 1. That's pretty obvious. And then for the x value, I just take my negative pi over 12, and again, I'm just going to add my pi over 6. Just add a quarter period, and that's going to put me at pi over 12. So this one is pi over 12 right there, okay? And then at 3/4 of the period, I know I'm going to be at my minimum, right? And the minimum is negative 5. So I'm going to put a negative 5 in there, okay? And for this guy, I just take my pi over 12 and I add another quarter period, so pi over 6. And that's going to give me this pi over 4. So this is pi over 4, comma, negative 5. Then to get my last point here in this cycle, what I would want to do is add pi over 4 and pi over 6. That's going to give me 5 pi over 12. And I know the y value, that would have been an x-intercept. It's been shifted down by a unit. So instead of 0, it's going to be negative 1. Okay, so that's how you can get those 5 points. So this one, this one, this one, this one, and this one. And so that's going to be one cycle or one period of this graph. Just connect these guys with a smooth sine wave, and you're basically good to go. If you want to go to the right or to the left, you're just making repetitions of that one cycle. All right, now that we've mastered graphing the sine function, we're going to move on now and talk about graphing the cosine function. So the reason I spent all of the lesson so far on the sine function, it's a little bit easier to start with one function, learn all of the graphing transformations, and then take that knowledge and apply it to the other one. Okay, it's the same process. So if I think about f of x is equal to the cosine of x, how will this graph be different from f of x equals the sine of x? Well, basically you take your sine graph and you do a phase shift of pi over 2 units to the left, and you're going to have your cosine graph. You'll see that in a moment. So all we really need to think about is how this guy is going to be different in terms of the 5 key x values that you pick. What are the y values there? How is that going to be different? Once you memorize that, you just take the knowledge from the sine graph that you learn, those strategies, those techniques, and you apply it to the cosine graph, and you're good to go. So I'm just going to think about these quadrantal angles. We start with an x value of 0 would produce a cosine value or a y value of 1, okay? And then as we go to pi over 2, we're decreasing, right? So we're going to end up at 0 when our x value or our angle is pi over 2. Then as we continue to pi, we're decreasing from 0 down to negative 1, okay? And then as we go from pi to 3 pi over 2, we are increasing from negative 1 up to 0, okay, so right there. And then lastly, as we go from 3 pi over 2 to our 2 pi, right, we're making one full rotation, we are increasing from 0 to 1. Okay, so you can refer to this table if you want to have some notes on that. Now, when we think about this guy over one period, so f of x is equal to, I'm going to put cosine of x. I'll say that 0 is less than or equal to x, which is less than or equal to 2 pi. So this is just one period. You want to think about how these points are going to be different from the sine graph. If you memorize those differences, you're basically good to go. Your period here is the same. It's still going to be 2 pi. We should know that from the unit circle. Now you'll notice that you have a maximum here and a maximum here. And this, if I draw a line down the middle, I want you to notice that you could take this point and reflect it across this line and you'd end up with this point. Remember, that is an even function, right? So where f of negative x is equal to f of x. We've seen this with the squaring function, right? If you saw something like f of x equals x squared, doesn't matter if I plug in a 2 there, 2 squared is 4, or a negative 2 squared is also 4, you get the same y value, okay? So cosine is going to be an even function. We'll talk more about that in a moment. Okay, so another thing you'll want to think about is the fact that with the sine graph, remember, you had 3 x-intercepts. You had an x-intercept at the beginning, the middle, and the end, okay? Here, you only have 2 x-intercepts, and it's going to be at the quarter of a period and 3/4 of a period, okay? And then your minimum occurs at halfway. Okay, so you want to remember that you start at the maximum, you end at the maximum. Halfway through, you're at the minimum, okay? And a quarter way through and 3/4 way through, you're at the x-intercept. That's really all you need to memorize. You just take the other information from the sine graph and you're good to go. Now let's extend this to the left and right. So this is f of x equals the cosine of x. So here's going to be 1 period from here to here, okay? So 1 period. Again, this is just the sine graph that's been phase shifted to the left by pi over 2 units. Okay, that's all it really is. It's the same type of graph. Now, a couple of key things. This f of x equals the cosine of x. It's continuous across this entire domain. So just like with f of x equals the sine of x, again, the domain for each is going to be all real numbers. The period for each is going to be 2 pi. So that stuff's the same. The range is -1 to +1. That's the same. The x-intercepts, this is going to be different. So the x-intercepts is going to be of the form, you're going to have 2n plus 1 times pi over 2, okay? I should probably move this so it's a little bit more clean. Let me move this down there. And basically, n is any integer. Let me make that a little bit better because that's a little bit bad in terms of handwriting. Let's say n was 0. 2 times 0 is 0, so you'd have 1 times pi over 2. So that's this x-intercept here, okay? If you put in a 1, you'd have 2 plus 1 is 3. 3 times pi over 2 is 3 pi over 2, so on and so forth. Now, the last thing I want to do is talk about the fact that this guy is an even function. We already saw that, right, when I basically drew a vertical line at x equals pi. But you should know that basically with cosine of x, you could say that the cosine of negative x is equal to the cosine of x. We can go back to the unit circle, and you can grab a value real quick. Let's say you grab pi over 6, and you can say the cosine of pi over 6 is equal to the cosine of negative pi over 6. Really easy to prove that. Cosine of pi over 6 is square root of 3 over 2. And the cosine of negative pi over 6, I'm just rotating clockwise now. So I'm coterminal with 11 pi over 6. So this would be square root of 3 over 2 as well. Okay? So cosine is an even function. Okay, let's take a look at one example with graphing cosine. I'm going to put all the different transformations into this guy. Again, if you can do this for sine, you can already do it for cosine. Now, what I'm going to do is rewrite this to start. You have f of x equals 3 times the cosine of 3x plus 2 pi over 3. Then you have this plus 2. So let me write f of x is equal to, I've got 3 times the cosine of, I'm going to go ahead and factor this 3 out. Again, I think this is the simplest way to identify the phase shift, but you don't need it, so it's up to you. So 3 times, inside the parentheses, divide everything by 3. 3x divided by 3 is x. Then plus, if I had 2 pi over 3, and I multiplied by a third, same thing as dividing by 3, this would be 2 pi over 9. Okay, close that down. And then don't forget your plus 2 at the end. Okay, so now that we have this set up, we can identify what's going on here. We know that this 3 out in front, the absolute value of that guy, which is just 3, is the amplitude. Okay, so that's going to be 3. Now with the normal cosine graph, just like a normal sine graph, it's going to tell you your minimum is at -3 and your maximum is at +3. But if you look at the graph that's already drawn, you see the minimum is at -1 and the maximum is at 5. So what's going on? You have this plus 2 at the end, okay, and that's giving you a vertical shift up. So instead of -3 for the minimum, you add 2 units and you get to -1. So if I think about my range, okay, the minimum is now going to be -1. The maximum, again, it would have been 3, add 2 units, now it's going to be 5. Okay, and we're going to use this in a little while when we start getting these points. Now, additionally, when I think about the period, it's going to be 2 pi divided by b. Now, b here is 3, so just 2 pi over 3. If you want the quarter periods, again, this is for us to get those x values. Well, it's just 2 pi over 3 multiplied by a fourth. So basically, this cancels with this and gives you a 2. So this is pi over 6. Okay, so we're going to have pi over 6 for the quarter periods. And then when we think about the phase shift, so let me put the phase shift in here, you have x plus 2 pi over 9. So again, if you have plus 2 pi over 9, I'm shifting to the left by 2 pi over 9 units. So that means I'm going to shift to the left by 2 pi over 9 units. Now, the last thing I want to put in here, and I'm running out of room, so let me just put it off to the side. My vertical shift, as we talked about earlier, I have a plus 2 here, so that's up 2 units, okay? So now that we've identified all these things from just looking at our function, we can go through and think about how our points would have moved based on the original cosine graph. So it's really, really easy, okay? Now, what I would say is that this guy, based on the original cosine graph, has been stretched vertically by a factor of 3 from that guy. It's been compressed horizontally by a factor of 1 over 3. It's always 1 over b. b is 3. So it's been compressed horizontally by a factor of 1/3. And then we've had a phase shift of 2 pi over 9 units left and a vertical shift up by 2 units. Okay, so that's all our different transformations. So if we go to our original cosine graph, remember, the cycle starts at the maximum. The x value is 0 and the y value is 1, okay? So based on this function here, I know I'm going to start at the maximum. The maximum is 5. So I know the y value for this first point is going to be 5. What's the x value going to be? Well, I'm just going to consider this phase shift, which is 2 pi over 9 units left. So 2 pi over 9 units left. So that would give me a negative 2 pi over 9, okay? And then comma 5. So that's going to be this point right up here, okay? That's going to be the first point we get. So this is negative. Let me put my 2 pi over 9, comma 5. Okay, so pretty easy to get that point. Now, when you go to get the other points, what I would suggest is just getting your y values first. They're really easy to figure out. Remember, at the beginning of the period and at the end of the period, you're at the maximum. So here's your beginning and here's your end. Okay, so you're going to be at the maximum. So let me put a comma here and then put a 5. Okay, so I know the y value there is 5. I know that halfway through I'm at the minimum. The minimum is negative 1. We already figured that out. So that's going to be right here. Let me put a comma and then negative 1. At a quarter way through the period and 3/4 way through the period, you would have had an x-intercept. But because we have this plus 2, or this vertical shift up by 2 units, now the y-coordinate is going to be 2. Okay, so for right here, the y-coordinate is going to be 2. And for right here, the y-coordinate is going to be 2. Again, if you find this confusing what I'm doing, you can always take your x values, plug them into the function and evaluate, and you can get your y values that way. This is just quicker for me and for most people as they sketch the graph. Now, to get these 4 missing x values, you already have the first one. You're just going to add quarter periods, okay? So I'm going to add pi over 6 to the existing x value. So negative 2 pi over 9 plus pi over 6 is going to give me negative pi over 18. So negative pi over 18. Okay, so that's going to be the x value for this point right here. Okay, so negative pi over 18, comma 2. Then as I get to my minimum, I add another pi over 6 to this negative pi over 18. And what I'm going to get is pi over 9. So this point would be pi over 9, comma negative 1. Then I add another pi over 6 to this pi over 9. And I'm going to get to 5 pi over 18. So 5 pi over 18, comma 2. And then lastly, I add another pi over 6. And I'm going to get to the x value for this point, which is going to be 4 pi over 9. Let me make that a little bit better. Okay, let me make that a little bit better. So 4 pi over 9, comma 5. Okay, so this would be one cycle, okay, for our graph. And again, if you want to keep going to the left or the right, you're just making repetitions of that one cycle. In this lesson, we're going to talk about graphing tangent and cotangent. All right, so in the last lesson, we talked about how to sketch the graphs for sine and cosine. And we found that the process is really not that bad. The main thing to understand when you're in this section is that you are not expected to make a perfect graph. You're just expected to know the key information and how you could sketch the graph if you had to. Generally speaking, we're always going to use computer software, either something that's online or a graphing calculator like a TI-83 to sketch our graphs. So with that being said, let's go through how to sketch the graph for tangent and cotangent. We're going to start with a different period. So basically we know that the period for sine and cosine is 2 pi. But when you work with tangent and cotangent, you need to know that the period is now going to be pi. That's extremely important, especially when we get to solving trigonometric equations. So something like the tangent of x is going to be equal to the tangent of x plus pi n, where n is any integer, and we would also say that x is a member of the domain. Remember that when you work with tangent, you have places where it's undefined. Then we have cotangent of x is equal to the cotangent of this x plus pi n, again, where n is any integer, and x is a member of the domain. So let me just quickly demonstrate that the period for tangent and also cotangent is going to be pi. You can show this with identities, but we haven't gotten that far yet. First off, I'm just going to pick something like pi over 6 for the angle. So this guy right there. And you know that if you want the tangent of pi over 6, you can find it as the sine of pi over 6 divided by the cosine of pi over 6. In other words, we should know that the tangent of x is equal to your sine of x over your cosine of x. So the tangent of pi over 6 is going to be equal to the sine of pi over 6, and then this would be divided by the cosine of pi over 6. So what would this be equal to? We know that the sine of pi over 6, again, that's going to be given by the y-coordinate right there, so that's 1/2. So let's write that. How do we divide fractions? We multiply by the reciprocal, so this is times. You would have the cosine of pi over 6, that's square root of 3 over 2, but you're going to find the reciprocal of that, so this is going to be times 2 over the square root of 3. And then basically the 2's are going to cancel. And let's say that this is 1 over the square root of 3. We want to rationalize the denominator here, so times the square root of 3 over the square root of 3. So this equals the square root of 3 over 3. So this is the square root of 3 over 3. Now, I want you to notice that if you add pi, or you could say if you rotate by pi, so I'm going to come over here into quadrant 3, and we're going to be at 7 pi over 6. Now, I want you to think about if I found the tangent, so the tangent of 7 pi over 6, what would I get? Well, you're going to find that you're going to get that same square root of 3 over 3. And the reason for that is you're dividing in terms of absolute values the same numbers. It's just that now you're going to be dividing a negative by a negative, which is also going to give you a positive. So in other words, this is going to turn into your sine value is negative 1/2, and then divided by your cosine value, which is negative square root of 3 over 2. We're going to, again, multiply by the reciprocal. So let's go negative. We're going to go 2 over the square root of 3. And so the negative times the negative will give you a positive. The 2's will cancel. So this would end up being 1 over the square root of 3, which we know if we rationalize the denominator, that's going to be the square root of 3 over 3. So you can see that the tangent of pi over 6 and the tangent of 7 pi over 6, that's the same. So that's one way you can demonstrate this. I'll show you with some other ones, just so you can see the stuff in quadrant 2 and 4. So that's where tangent is negative. So let's say you pick something like, let's say 2 pi over 3. So that guy right there. And that color doesn't show up so well, so let me do that like that. And again, if you add pi to this, so if you add pi, you're going to come into quadrant 4, and you're going to be at this 5 pi over 3. So it should be true that the tangent of 2 pi over 3 is equal to the tangent of 5 pi over 3, because again, I added pi. Every time I add pi, I'm coming back to the same tangent value. So let's just try that real quick. So we have the tangent of 2 pi over 3. That would be equal to the sine of 2 pi over 3, which is the square root of 3 over 2, and then divided by the cosine of 2 pi over 3, which is negative 1/2. So I'm going to multiply by the reciprocal, so times 2 over negative 1, and of course the 2's are going to cancel, and you have square root of 3 over negative 1. Let's just say that's the negative of the square root of 3. Then if I come down here to 5 pi over 3, again, if I look for the tangent of 5 pi over 3, it's going to be the same thing. I'm going to be dividing opposites. Here it was basically a positive sine value divided by a negative cosine value. But here it's going to be a negative sine value divided by a positive cosine value. Well, we know if we have a positive divided by a negative or a negative divided by a positive, I'm going to get a negative. So that's what's happening here. So this is just going to be my negative square root of 3 over 2. That's the sine value here, divided by the cosine value, which is positive 1/2. So again, I'm going to multiply by the reciprocal, so times 2 over 1. And let's go ahead and cancel this with this. And so you get negative square root of 3. So hopefully that gives you a little bit of insight into why the period is going to be pi. All right, so what we're going to do now is just look at the basic graph for tangent. We're going to do this by grabbing some ordered pairs and just sketching this guy from negative pi over 2 to pi over 2, with both of those guys being excluded. Before I show you the graph, I want to cover a few things that basically cause a lot of confusion when you first see these graphs. The first thing is we should remember that when we see a negative angle, we're rotating clockwise. In other words, something like negative pi over 2, that means I'm starting here and I'm rotating clockwise. So it's going to be this guy right here. It would be coterminal with 3 pi over 2. So this is negative pi over 2. Now, why does it say that it's undefined here? We know that the tangent of x is equal to, we have the sine of x over the cosine of x. Well, if I want the tangent of negative pi over 2, that would be equal to the sine of negative pi over 2 over the cosine of negative pi over 2. Since this negative pi over 2 is coterminal with 3 pi over 2, we could just take the value for sine and cosine from this guy right here. And so basically, you could say that this is equal to the sine of negative pi over 2, well, that's negative 1. And then the cosine of negative pi over 2, well, that's 0. What do we know about division by 0? It's undefined. So basically, you stop at this point and you would say that this is undefined. Undefined. So this would always be true whenever the cosine value is 0. So basically, this is going to happen at pi over 2, then 3 pi over 2, then 5 pi over 2, 7 pi over 2, 9 pi over 2, so on and so forth. But also you have to consider that would happen at negative pi over 2, negative 3 pi over 2, negative 5 pi over 2, so on and so forth. So a lot of books will cover this by saying that this guy is going to be undefined at odd multiples of pi over 2. So that's a good way to remember it. You could also write it as, if you want to do it this way, you could say that it's undefined at pi over 2, so this guy right here, plus pi n, where n is any integer. So basically, if it's a positive integer, then I'm rotating counterclockwise. So let's say I add pi, that's going to put me right here at 3 pi over 2. And if I add pi again, then I'd be at 5 pi over 2, then 7 pi over 2, so on and so forth. If n was a negative integer, well then basically now I have a clockwise rotation. So let's say I subtract pi, and I rotate clockwise like this, well now I'm not at 3 pi over 2, I'm going to be at negative pi over 2. And if I do that again and subtract away another pi, well now I'm going to be at negative 3 pi over 2, and so on and so forth. So all of those places it's going to be undefined because we're going to have a cosine value of 0, and division by 0 is undefined. Now the other thing you need to think about is that this guy is going to be 0 when the sine value is 0 and the cosine value is not 0. So something like, let's say, at 0, you have a sine value of 0, and the cosine value is 1. Then at pi, you have a sine value of 0, and a cosine value of negative 1. So basically for this, you could say that the tangent value is going to be 0 at pi n, where n is any integer. In other words, you could start here, and you could add pi, and you would get to pi. You could add pi again, and you would get to 2 pi, and then 3 pi, and then 4 pi, so on and so forth. And also, if you wanted to start here and rotate clockwise, so if you wanted to subtract pi away, well now I'm going to be at negative pi. Then if I do that again, I'm going to be at negative 2 pi, then negative 3 pi, so on and so forth. So basically that's where you're going to have a tangent value of 0, or you could say where your x-intercept is going to be. And you can see on the table that we've made that we do have this 0, 0. Okay, so let's look at a basic sketch for y equals tangent of x. So just using those points that we just had in our little table. So you have something like negative pi over 3, comma, negative square root of 3. So that would be this point right here. Then you have negative pi over 4, comma, negative 1. So that'd be this point right here. So this point is actually one we're going to focus on. It'll be important for us later on. Then we have negative pi over 6, comma, negative square root of 3 over 3. So that's this point right here. Then we have our 0, 0. So that's our x-intercept. And we'll focus on that one later on. Then you have your pi over 6, comma, square root of 3 over 3. Then you have your pi over 4, comma, 1. Again, this is one we're going to focus on. And then we have our pi over 3, comma, square root of 3. So that's going to be this guy right there. So one of the things to focus on here is you do have a vertical asymptote at this negative pi over 2 and then also pi over 2. And that's being created because, again, at negative pi over 2 and pi over 2, you have division by 0, which is undefined. So we've seen this previously in our course. When we look at something like y equals 1 over x, well, we know that if you plugged in a 0 for x there, this is undefined. So if you look at the graph of that, you're going to end up with a vertical asymptote at x equals 0. So here, when you have y equals the tangent of x, which you could really write as the sine of x, so the sine of x over the cosine of x to make it more clear. Well, again, where this is 0, at negative pi over 2 or pi over 2, something like that, 3 pi over 2, 5 pi over 2, 7 pi over 2, so on and so forth, well, you're getting division by 0, so you're getting these vertical asymptotes. Now, when you think about the behavior, as this guy right here approaches pi over 2, coming from the left. So coming from the left, basically as we approach this x value of pi over 2, this guy is going to increase without bound, as they say, so approach positive infinity. So I have another little table for you. A lot of books will show this. So basically at an x value of 0, we get a y value of 0. At pi over 6, you get about 0.58. That's just approximating square root of 3 over 3. At pi over 4, you get 1. At pi over 3, you get about 1.73. That's approximating the square root of 3. And then we have 1.5 is about 14.10. 1.53 is about 24.50. 1.57 is about 1,255.77, and then this 1.5707 is about 10,381.33. And then notice that as you get really close to pi over 2, so 1.570796, you get 3,060,023.31. So you can get as close to this as you want, you just can't touch it. When you actually get to pi over 2, you're going to get undefined. But as you get closer and closer to it, this number is going to get larger and larger. So again, it's going to approach positive infinity, or what they'll say is increase without bound. Now, similarly, as you approach negative pi over 2, coming from the right, this guy is going to decrease without bound. So basically, it's going to approach negative infinity. All right, so just like we saw with graphing sine or cosine, after we did one cycle of the graph, we were able to continue that to the left or to the right as much as we wanted. So here I have y equals tangent of x. So I've extended this to the left and to the right a little bit, just so you can see a little bit more. So basically, this is what we graphed already. So from negative pi over 2 to pi over 2, we see that we have a vertical asymptote at negative pi over 2, and then also another one at pi over 2. Those are what we call consecutive vertical asymptotes. So when you graph a variation of y equals tangent of x, you're going to first find those guys. I'll tell you how to do that in a moment. And then basically you have these 3 points. So this one right here is at a quarter of the way through. And let me just label this as a for right now. So a, let's just say that's negative pi over 4, comma negative 1. That's definitely something you want to memorize. Then let's call this b. This is going to be the halfway point, or the midway as a lot of books call it. That's your x-intercept, so that's 0, 0. And then let's call this point c. So that's 3/4 of the way through. So basically that point is pi over 4, comma 1. So you can use these points to basically graph any variation of y equals tangent of x. If you want these points here or wherever it is, if you just want this one right here, remember the period for tangent is pi. So I could take the x value here. Let's just call this point D. Let's call this point E. And let's call this point F. So if I wanted those, let's just go ahead and say that for point D, well, the y value is going to be the same. All I have to do is add pi to the x value. So negative pi over 4, plus pi, so 4 pi over 4 to have a common denominator, and that's going to be 3 pi over 4. So this would be 3 pi over 4, and then comma negative 1. And then for E, I know that basically I would just take 0 and add pi, so that would be pi, comma 0, y coordinate staying the same. And then this is going to be for F. Again, I'm just going to take this pi over 4, so pi over 4. I'm going to add pi, so 4 pi over 4, so that's 5 pi over 4. And then basically, you're going to have the same y coordinate, so it's still going to be 1. And you can basically use that process to extend the graph to the left or to the right as much as you want. All right, so just some information that you need to know. So for the tangent function, the domain contains all real numbers except odd multiples of pi over 2. Some books will write that as pi over 2 plus pi n, where n is in the integer. So basically, it's just telling you things like pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. You could also have negative pi over 2, negative 3 pi over 2, so on and so forth. We have f of x is equal to tangent of x. You could also write y equals tangent of x is discontinuous at odd multiples of pi over 2. So basically, we've seen that the graph contains vertical asymptotes at those values. The x-intercepts are of the form x equals pi n, where n is any integer. We know that that's because that's where the sine values are 0, and 0 divided by something that's not 0 gives you 0, so that's why that occurs. The x-intercept occurs at half of the way between consecutive vertical asymptotes. So if we're using y equals tangent of x over that interval that we talked about, so from negative pi over 2 to pi over 2, with both being excluded, that's going to occur at 0, 0. Then we have our point on the graph that's a fourth of the way between consecutive vertical asymptotes. This is going to have a y coordinate of negative 1. So again, using that example, y equals tangent of x over the interval from negative pi over 2 to pi over 2, both excluded, we have that negative pi over 4, comma negative 1, and then the point on the graph 3/4 of the way between consecutive vertical asymptotes has a y coordinate of 1. So again, using y equals tangent of x over that interval, negative pi over 2 to pi over 2, both being excluded, we have that pi over 4, comma 1. So we already know that the period is pi, and then there are no minimum or maximum values. So that's important. we saw that the range is from negative infinity to positive infinity. So that tells us that the graph has no amplitude. So that's important because you might get that on your test. It might ask you for the amplitude. Remember that when you think about the amplitude, we learned in the last lesson when we were graphing sine and cosine, that's half the difference between the maximum and minimum values. Well, here again, there are no minimum or maximum values, so you're not going to have an amplitude here. Then we can also say the graph is symmetric with respect to the origin. Remember, that tells us we have an odd function. So the tangent of negative x is equal to the negative of the tangent of x for all x in the domain. Again, f of x equals the tangent of x is an odd function. All right, let's talk about the steps involved with graphing the tangent function. So what I'm going to do is give you a simple model here. And then if we get something that's a little bit more challenging, we can just modify our steps. So the first thing is we have y equals a times the tangent of bx minus c. And we're specifically going to say here that b, which is the coefficient of x, is greater than 0. Of course, we'll see scenarios where b is negative, and I'll show you how to deal with that with identities. For right now, let's go ahead and talk about the period. So what is the period? Again, when we think about this from our sine and cosine lesson, we know that if we had something like y equals the sine of bx, well, the period here, so the period here, was the standard period for sine, which is 2 pi, divided by b. Well, it's a similar thought process here. When you have y equals the tangent of x, the standard period is now pi. Not 2 pi, but pi. So let me put that off to the side. So y equals the tangent of x. The period is pi. So we know that. Well, here, the period for this guy right here, because you have b that's multiplying x, it's going to be pi over b. Now, I have a little sample illustration here to go through the procedure. So basically, the first thing you're going to do, you're going to find these two consecutive vertical asymptotes. And the way you do that is you go back to, again, y equals the tangent of x. We know that we generally graph one cycle from negative pi over 2 to pi over 2, with both being excluded. So you have x equals negative pi over 2, and you have x equals pi over 2. So you could say that one cycle occurs where x is greater than negative pi over 2 and less than pi over 2. So this negative pi over 2 and pi over 2, those are consecutive vertical asymptotes. Now, we don't have an argument of x, we have an argument of bx minus c. So we just have to adjust this. Let me get rid of this real quick. We're going to use the same thought process, though. We're going to say that we're going to do one cycle where bx minus c is greater than negative pi over 2 and less than pi over 2. And we can find the vertical asymptotes by saying that bx minus c is equal to negative pi over 2. So that would be one of them. We'll put and bx minus c is equal to pi over 2. So that would give you this guy and this guy. So the two consecutive vertical asymptotes that you're looking for. Once you have that, you need to find these 3 points. So you're going to have one that's a quarter of the way, halfway, and 3/4 of the way. The way you do that is you find your quarter period, just like we did with sine and cosine. And so basically, if the period is pi over b, well, you can multiply that by 1/4, and you could say that the quarter period is going to be pi over 4b. So you take your leftmost vertical asymptote, so that's x equals some number. You take that value and you add pi over 4b to that, and you're going to get the x value for the quarter of the way point. Then you add the quarter period, you get the halfway point. Then you add the quarter period, you get the 3/4 of the way point, and you could add a quarter period to get the next vertical asymptote if you wanted to, but again, you should already know what that is because you already set up those two equations. So the main thing is that you just have to find the x values there. The y values are very easy to find. You can just use the fact that at a quarter of the way through, the y coordinate is negative a. So whatever this is, it's the negative of it. Halfway through, it's going to be 0, and then 3/4 of the way through is just going to be a. Again, going back to what we saw earlier when we did y equals the tangent of x, remember I told you to memorize these 3 points. You have negative pi over 4, comma, negative 1. Well, you could put a 1 here if you want for clarity. Well, it's the negative of 1. That's how you get that y coordinate. Then you have another point, which is 0, comma, 0. That's just your x-intercept. And then you have another point, which is pi over 4, comma, positive 1. Okay, so positive 1 there. So I would just memorize those 3 points from this basic tangent function. If you do that, you're going to be good to go with any graph that you come across. All right, let's take a look at an example with the tangent function. So we have f of x equals 2, and then tangent of 2x plus 2 pi over 3, and then plus 1. So what I'm going to do is just use the procedure that we just talked about. There's alternative approaches. When I get done with this problem, I'll show you another way that you could do it. I'll just do a few points using graphing transformations only. The first thing is to think back to what we talked about a moment ago. If we're graphing something like y equals the tangent of x, generally speaking, if you're graphing that over one period, or if you say you want to graph one cycle of this guy, well, we know that we're going to do x is greater than negative pi over 2 and less than pi over 2. We know there's a vertical asymptote at negative pi over 2 and also at pi over 2 because, again, the tangent of negative pi over 2 and the tangent of pi over 2 is going to be undefined because we'd have division by 0. So what you want to do is set up an inequality here. The argument is not x like we have here. The argument is 2x plus 2 pi over 3. So this guy right here just gets plugged in for this right here. So you're going to set up the inequality. Let me get rid of this. Where you say 2x plus 2 pi over 3 is greater than negative pi over 2 and less than pi over 2. And I'm just leaving myself some space because we're going to multiply in a moment. So we're going to solve this inequality for x. So this is the goal right there. So we do have some fractions involved. I would personally like to clear those. Some people don't mind them, but I find that working with fractions is very tedious. So what I would do is look at the denominator here of 2, then you have a denominator of 3, then a denominator of 2. So the least common denominator is going to be 3 times 2 or 6. So just multiply each part here by 6, and then you can get rid of the fractions and you won't have to deal with them. So basically 6 divided by 2 would be 3. And so you'd have negative 3 pi there. So this is less than. This gets distributed to each guy. So 6 times 2x is 12x. And then plus, you have 6 times 2 pi over 3. So this 6 would cancel with this 3 and give you a 2. 2 times 2 pi is 4 pi. So let me write that there. And then basically, this is less than. 6 would cancel with the 2 and give me a 3. So 3 times pi is 3 pi. At this point, again, if you're trying to isolate x, what I would do is subtract 4 pi away from each part. So let me do that over here. This is going to cancel. On the left, you have a negative 4 pi minus 3 pi. That's negative 7 pi. This is less than. In the middle, you're going to have 12x, which is less than. On the right, you can have 3 pi minus 4 pi. That's negative pi. Again, if you want to isolate x in the middle, just divide each part by 12. So divide by 12, divide by 12, and divide by 12. So this right here is going to cancel. Let me slide down here a little bit. And you're going to have negative 7 pi over 12 on the left. And this is less than x, which is less than negative pi over 12. So this is telling me that my function is going to go through one cycle from negative 7 pi over 12 to negative pi over 12, where negative 7 pi over 12 and negative pi over 12 are my two consecutive vertical asymptotes. And let me come down to this page right here. Let me go back up and let's talk about the period. So what is my period? And then I'm also going to need to know what is my quarter period. So the period, again, if you're looking at y equals the tangent of x, well, the period is just going to be pi. If I change this to y equals the tangent of bx, well, now, provided that b is positive, again, if you don't have a positive b, you could just use absolute value bars, but provided that b is positive, you'd say the period is pi over b. So you're just dividing by whatever the coefficient of x is. So here, we have a coefficient of x that's 2, so the period is pi over 2, and then the quarter period is pi over 2 times a fourth, so that's going to be pi over 8. So this is pi over 8. If you want to know if you got the right period, let's come down here and paste this in and just put a little border around it, you can actually subtract. So you're going to go larger minus smaller, and you should get pi over 2. So negative pi over 12. So that's for this guy right here. And then you're going to go minus this negative 7 pi over 12. Convert this into plus. Minus a negative is plus a positive. So this becomes, you could write negative 1 there. So negative 1 pi plus 7 pi, that's going to be positive 6 pi over 12. And of course, this simplifies to pi over 2. So that confirms the period right there. So you have two consecutive vertical asymptotes. Let me put vertical asymptotes here. You have one at x equals negative 7 pi over 12. And then the other, I'll just put and here, x is equal to negative pi over 12. If you come to the graph, and I have a link for you on Desmos if you want to get something that has more detail. I have all the points labeled for you if you want to click on that. This is what we've found so far. So this is the vertical asymptote, And this is the leftmost one that we found. So x equals negative 7 pi over 12. Again, if you plug that in for x there, you're going to get undefined. So that's why you're getting a vertical asymptote there. Then this guy right here is going to be our x equals negative pi over 12. Again, if you plug that in for x there, you're going to get undefined. So you're getting this vertical asymptote here. Our next goal is to figure out what is this point, and this point. So this is the quarter of the way through. This is halfway or midway, and this is 3/4 of the way through. So let me come back and let's think about how we can use this information. So the first thing is you can find your x values by just adding quarter periods. So you can start with this one, x equals negative 7 pi over 12, add the quarter period of pi over 8, and you just keep doing that to get the next x value and the next x value and the next x value. The y values you can either plug into the function or you can use graphing transformations. So I'll show you both. Let me go ahead and grab this real quick. So you have negative 7 pi over 12, and then plus pi over 8. I'm not going to have enough room to do this on the sheet, so I'm actually going to go to another page. If you're trying to find your x value for the first quarter point, let's multiply this by 3 over 3. And let me slide this down. I'm going to multiply this by 2 over 2, just so we can have a common denominator. If you notice, you have a denominator of 12 and a denominator of 8. So this is basically 2 squared times 3. And this right here is 2 cubed. So basically the LCD is going to be 24. It's going to be 8 times 3. So this right here would turn into negative 14 pi over 24, just multiplying 2 times negative 7 pi, that's negative 14 pi, and then 2 times 12 is 24. And then plus over here, 3 times pi is 3 pi, and this is over 8 times 3, that's 24. So if you do this, negative 14 pi plus 3 pi, that's negative 11 pi, and this is over 24. Okay, let me write this right here. So for my first quarter point, the x value is negative 11 pi over 24. The quarter period, we have that listed as pi over 8, but again, we could see that we could write that as 3 pi over 24, so we have a common denominator. So go ahead and add here. So negative 11 pi over 24 plus 3 pi over 24, that would be negative 8 pi over 24. You can simplify that, but I wouldn't do it yet. Let's come down here. So this is for the halfway or midway. So basically, this is going to be negative 8 pi over 24. And if you simplify that, 24 divided by 8 is going to be 3, and 8 divided by 8 is 1. So this becomes negative pi over 3. Okay, then we want our 3/4 of the way point. So start with this. And again, just add a quarter period. So this is plus 3 pi over 24. And let me slide this down over here. So this should be negative 5 pi over 24. Just doing negative 8 pi plus 3 pi, that's negative 5 pi over the common denominator of 24. So negative 5 pi over 24. Now coming to the graph, we can see that for the first quarter point, the y value is going to be negative 1. For the halfway point, it's going to be positive 1. And then for the 3/4 of the way point, it's going to be 3. Now, how could we get that? Well, essentially, you could plug into the function or you could use graphing transformations. Let me just show you with this one right here that you could do it that way, and then I'll do the graphing transformations because it's a little bit faster. So coming back up here, you would want to say, what is f of negative 11 pi over 24? So you're just plugging in. So this equals 2 times the tangent of, you have 2 times negative 11 pi over 24. You're just plugging this right here in for x right there. So that's all you're doing. And then we'd say plus 2 pi over 3, and then plus 1. You can think about this canceling with this and giving me a 12 down here, and then I could multiply this. Let me scooch this down a little bit. I could multiply this by 4 over 4, so I have a common denominator. So this would be negative 11 pi over 12, and then plus this would be 8 pi over 12. So let me write that in. And then you would have negative 11 pi plus 8 pi, that's negative 3 pi. So you'd have negative 3 pi over 12. Negative 3 pi over 12. And of course, that's going to simplify to negative pi over 4. So negative pi over 4. We know that the tangent of negative pi over 4 is negative 1. So basically, this becomes 2 times negative 1 and then plus 1. So 2 times negative 1 is negative 2, and then negative 2 plus 1 is negative 1. So this equals negative 1. Again, if you go to the graph, you can clearly see the y-coordinate here is negative 1. So let me put negative 1 in right there. Now, what's the other way to do this? Because that's pretty slow. Well, you could have used graphing transformations. In other words, you know that on y equals the tangent of x, you have these points which are for the quarter of the way through, again, it's negative pi over 4. comma, -1. And then for halfway through, it's going to be 0, 0. That's your x-intercept. And then for 3/4 of the way, you're going to have pi over 4, 1. Well, what's happening in terms of the vertical transformations? Well, you have this 2 out in front. That's giving me a vertical stretch by a factor of 2. And then you have this +1 right here, which is going to give me a shift up by 1. This is done first, and this is done second. So in other words, if I take this, let me move this down here a little bit so it fits. So if I take this right here, this y-coordinate of -1, and I multiply by 2 first, and then I add 1 second, well, that's -1 times 2, that's -2, and then -2 plus 1, that's -1. If I go through this one, and I go 0 times 2 plus 1, well, 0 times 2 is 0, plus 1 is 1, +1. And then if I look at this one, I have 1 times 2 plus 1, so 1 times 2 is 2, 2 plus 1 is going to be 3. And that's exactly what we saw. If you look at for the halfway point, well, basically the y-coordinate is 1. If you look at the 3/4 of the way point, the y-coordinate is 3. Once you know those y-coordinates, when you go to the right or to the left to extend the graph, those are always going to be the same. So for the first quarter point, it's always going to be -1. For the halfway point, it's always going to be +1. For the 3/4 of the way point, it's always going to be +3. So you only need to figure out the x coordinates for the vertical asymptotes and for the points that you're getting. And you can just do that by continually adding quarter periods. In other words, in terms of getting the x values, you could start here, add a quarter period, 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 and you would just keep getting to the next guy. So let's come through here and just put that this is 1, and then put that this is 3. So those are your points. Again, you can get more points if you want. That's going to be up to you. I left you a very detailed graph on Desmos where all the points are filled in. But basically, I can come through here and try to fill this in. It's going to be really tight. This point right here, let me just arrow to it and say it's -11 pi over 24, and then comma, -1. Then you have your negative pi over 3, 1. So this right here is negative pi over 3, comma, +1. And then this one right here is negative 5 pi over 24, comma, 3. So again, you can click that link and go to Desmos and see all of these points. I've labeled them for you if you want to get more detail. All right, before I move on to the next problem, I want to show you this using only graphing transformations. This is something you should be aware of. In some cases, it's faster. You may prefer to do it this way, but generally speaking, it's very error prone because a lot of students have trouble with horizontal transformations. So things that affect the x coordinate. So let's just look at f of x equals 2 tangent of 2x plus 2 pi over 3 and then +1 and compare it to your f of x is equal to your tangent of x. So with this one, let me actually grab this real quick and let me come down here and paste this in. You have your basic points, which we already know at this point. Let me put a little border here. The first quarter, so basically that's going to be negative pi over 4, comma, -1. You have your halfway, that's going to be 0, 0. And then you have your 3/4, and basically that's going to be pi over 4, 1. So you think about the transformation, so you're going to have a new x coordinate and a new y coordinate. Of course, you also have the asymptotes to consider. So for that, you just have to think about the x. So you'd have x is equal to negative pi over 2, and so you'd have x is equal to pi over 2. And these right here, these are the vertical asymptotes. So let's come back up. And the first thing I would do is I would factor this. So I would say f of x is equal to 2 times the tangent of, pull out that 2 there. It's just going to make the phase shift a lot easier to find. So pull that out, and then you're going to have x plus pi over 3. And basically close that down and say this is +1. I always like to check this. So 2 times x is 2x, and then plus 2 times pi over 3 is 2 pi over 3. So that's good to go. So here is where it starts to get a little bit confusing. You have transformations that are happening to the y, those are the vertical transformations, and you have transformations that are happening to the x, those are the horizontal transformations. The vertical transformations are very straightforward. If you have something like a times, let's say, f of x plus b, so let's say g of x is equal to this, we already know that basically this right here is a vertical stretch if a is greater than 1, and it's a vertical compression, or sometimes you'll say a vertical shrink if a is between 0 and 1. Then for this one right here, this b, this is giving me a shift up if b is positive and a shift down if b is negative. So hopefully you know that already. And in terms of the order, we follow just the order of operations. You do multiplication before you do addition in the order of operations. So this is done first and this is done second. So if I look at this is done first, and this is done second. So we know that for the y coordinates, again, we saw this earlier, you're going to multiply by 2 first, and then you're going to add 1. So if we think about those points, and let me slide this over so this fits. When I go over here and I do my transformation, actually, let me move this to another page because I don't think it's going to fit the way that it is. Basically, you can get the y values. Again, you multiply by 2 first. So -1 times 2 is -2. Then you add 1. So -2 plus 1 is -1. And then for this one, 0 times 2 is still 0. Then you add 1, so that's 1. And then for this one, 1 times 2 is 2, plus 1, so that's 3. So that's very straightforward. It's done almost instantly. Now let's come up and let's think about the harder guy, which is going to be what's happening to the x coordinates. Basically, what are the horizontal transformations? We know that if we have something like, let's say g of x is equal to f of, let's go ax here. This is going to be if a is greater than 1, you have a horizontal compression, or you could say a horizontal shrink. And then if a is between 0 and 1, now you're going to have that horizontal stretch. So it's always the opposite of what you think. So basically here, when you think about that 2, well, that's something that's greater than 1. So that is going to give me a horizontal compression, or you could say a horizontal shrink, however you want to say that. Now, this is the confusing part because there's different terminology. Some people will say that there's a horizontal compression by a factor of 2. If you want to say that, that's fine. Typically, I'll say it that way. Other people will say that it's been horizontally shrunk by a factor of 1/2. Whatever you want to use in terms of the terminology, just realize that you're going to either be dividing by 2 or multiplying by 1/2. Whatever you want to do there and whatever you want to say, just realize what's happening. Now, this part right here, this is your phase shift. And again, it's the opposite of what you think. If you have x plus pi over 3, that means that I want to go pi over 3 units to the left. I want to go minus pi over 3. It's always the opposite of what you see. So what you would want to do here is actually do this one first and then this one second. So why is that the case? If we were thinking about the order of operations, then you would want to do what's inside the parentheses first, and then what's outside, which in this case would be multiplication, second. But again, on the inside, you have to reverse everything. This looks like I'm multiplying by 2. Well, I have to do the opposite of that. I have to divide by 2. This looks like I'm adding pi over 3. I have to do the opposite of that. I have to subtract pi over 3. And then the same thing happens with the order of operations. It has to go in reverse now. So basically, it has to be this one first and then this one second. So if we think about all the x values, the first thing you're going to do is you're going to multiply by 1/2, or again, you could divide by 2. And that's because you have to undo this part right here. You undo multiplication by 2 by dividing by 2 or multiplying by 1/2. Then the second guy here that you're going to do, you're going to subtract away pi over 3. So you can just write subtract pi over 3, or you could put add negative pi over 3. So this is what we need to do to each x to get those x coordinates. So let me come down here. We'll do it to the asymptotes first. So if you start with negative pi over 2, and you multiply by 1/2 first, that's going to be negative pi over 4. And then in step 2, you're going to take negative pi over 4. You're going to need a common denominator, so let's multiply this by 3 over 3 now. So that would be negative 3 pi over 12. So you can have negative 3 pi over 12. And you're going to subtract away pi over 3. Let's write that as 4 pi over 12, just getting a common denominator. If you do the subtraction, you're going to get negative 7 pi over 12. Notice that matches exactly what we got right here when we solve the problem in a different way. So you get x equals negative 7 pi over 12. The other guy is going to be x equals negative pi over 12. So let me erase this. And then for this one, again, all you're going to do, you're going to multiply by 1/2. So pi over 2 times 1/2, that would give me, let me actually show this. So pi over 2 times 1/2. This would be pi over 4. So that's done first. And then once you have that, you subtract away pi over 3. So you have pi over 4, and then minus pi over 3. Again, get a common denominator. This would be multiplied by 3 over 3. So this would be 3 pi over 12. Multiply this by 4 over 4. So this would be 4 pi over 12. So 3 pi minus 4 pi would be negative pi over the common denominator of 12. So negative pi over 12. Again, as I just told you, x equals negative pi over 12. That's your other vertical asymptote that we found earlier using the other approach. And we'll arrow to this. So the vertical asymptotes here, for this guy, you would have x is equal to negative 7 pi over 12, and then x is equal to, let me put and in there, negative pi over 12. So that's how you could find that using the graphing transformations only. Let me go ahead and copy this real quick. And let me come down here and paste this in. For getting the x coordinates for these 3 points, again, you just follow the same procedure. Multiply by a half, then subtract away pi over 3. Negative pi over 4 times a half, negative pi over 4 times 1/2, that's going to be negative pi over 8. So once you have that, you're then going to subtract away your pi over 3. So minus pi over 3. We need a common denominator here. That's what makes it take so long. So let's say this is negative 3 pi over 24, just multiplying this by 3 over 3, and then minus, let's multiply this by 8 over 8, so 8 pi over 24, and we get negative 11 pi over 24. And we know that's the case, so negative 11 pi over 24. Again, if you check with what we did earlier, here's negative 11 pi over 24, comma negative 1. The next one's a little bit easier because you're working with 0. So 0 times a half is still 0. So then you just need to subtract away pi over 3. So this becomes negative pi over 3. And so negative pi over 3, comma 1. Again, here's your halfway point. So negative pi over 3, comma 1. And then for the last one, you have pi over 4 times 1/2. So that's done first. So this would be pi over 8. So then we have to subtract away pi over 3 from that. So you have pi over 8 and then minus pi over 3. Again, just get a common denominator. I'm going to multiply this by 3 over 3. So this is 3 pi over 24. And then minus, you multiply this by 8 over 8. So this is 8 pi over 24. And this gives me negative 5 pi over 24. So this is negative 5 pi. Let me make this 5 better here. Over 24, comma 3. And let me show you that real quick. Here's your negative 5 pi over 24, comma 3 that we found earlier. So of course you can use this approach. Many students like it because it's a little bit faster, but you really have to understand all the different graphing transformations, particularly what's being done to x and what is the correct order. So if you have that down, then you could use this method. In some cases, it's a little bit faster. All right, let's take a look at another example with tangent. So here we have f of x equals the tangent of x over 2 minus 5 pi over 4, and then plus 1. So again, you can use the book procedure, the one that I started out with, or you could use graphing transformations. It's really up to you. I'll do this one both ways again. And then for the ones that we're going to do with cotangent, we'll have 2 examples. I'll just pretty much stick to the book method for those. So let's start off with our book method. Again, you're going to take this right here, the argument for the tangent function, and you're going to say x over 2 minus 5 pi over 4. And you're going to first say that this is greater than negative pi over 2 and less than pi over 2. So your goal is to solve for x. So we want to solve for this guy right here. So what you could do, again, if you have fractions involved, is just clear them first. It just makes your life a lot easier. And so what you see is you have a denominator of 2, 2, 4, and 2. So the least common denominator would be 4. So just multiply everything by 4 here. And let me do that like that and like that. So this 4 would cancel with this 2 and give me a 2. 2 times negative pi is negative 2 pi. So this is less than. 4 would cancel with 2 and give me 2. 2 times x is 2x. And then minus, these 4s would cancel. So you have 5 pi. And this is less than. 4 would cancel with 2 and give me 2. 2 times pi is 2 pi. Again, if I'm trying to solve for x, what do I do? Well, first, I would add 5 pi to each part. So let's go ahead and do that. And let me move this in a little bit more, like that. So on the left, 5 pi minus 2 pi is going to be 3 pi. So this is less than 2x. Let me show this as canceling, which is less than 2 pi plus 5 pi. That's going to be 7 pi. Again, if you want to isolate x here, just divide each part by 2. So let's go ahead and say this is divided by 2, this is divided by 2, and this is divided by 2. So this would cancel. Let me slide down here a little bit. And so now we have x is greater than 3 pi over 2 and less than 7 pi over 2. And let me come down here to a fresh page. So again, just getting the information for the consecutive vertical asymptotes. So vertical asymptotes, you're going to have x is equal to 3 pi over 2. And then you're going to have x is equal to 7 pi over 2. So if you want to come to the graph, again, I gave you a link for a more detailed version on Desmos. This is your x equals 3 pi over 2. And then this is your x equals 7 pi over 2. So far we have that. But we need these 3 points. Again, you're quarter of the way, halfway, 3/4 of the way. The first thing is we do need the period. So what is the period? Let's go back up. So this right here is x over 2. You could really write that as 1/2 times x. So you could say this is f of x is equal to the tangent of Let me factor this because we're going to do this with all graphing transformations in a little while, so that'll already be done. Let me pull out a 1/2. So inside you'd have x minus. So then for this part right here, if you pull out a 1/2, it would be 5 pi over 2. Close that down, close this down, and then plus 1. Again, if you want to check this, 1/2 times x is 1/2 x, or x over 2 if you want to write it that way. Then you have minus and minus, and then 1/2 times 5 pi over 2 would give me 5 pi over 4. So that checks. All right, so if we look at it now, you have this 1/2 here. So the period is going to be pi divided by 1/2. So pi divided by 1/2. So you can go pi over 1 times 2 over 1, which is 2 pi. Okay, so now we know that the period is 2 pi. And then the quarter period, again, you just divide this by 4 or multiply it by a fourth. We know that 2 pi over 4 would be pi over 2. That's your quarter period. So if you want to get your x values, you're going to start with this 3 pi over 2, and then you're going to add quarter periods. Let me come down here. So let me start with 3 pi over 2, and I'm going to add pi over 2. And then basically that's going to give me 4 pi over 2. So let me write this as the quarter point, so the first quarter. You're going to have 4 pi over 2, if you want to do that now, is going to be 2 pi if you simplify. But keep it like this for adding. So for the next guy, you're going to go 4 pi over 2 plus pi over 2. That way you don't have to worry about getting a common denominator. This will give me 5 pi over 2. So for the halfway point, or the midway as a lot of books say, you have 5 pi over 2 for the x-coordinate. And then we'll do this one more time. So 5 pi over 2, and then plus pi over 2. This is going to be 6 pi over 2, which of course is 3 pi. So let's say that this is the 3/4 point, and basically the x value there would be 3 pi, just doing 6 pi divided by 2. Okay, we don't need this anymore. We have what we want. And basically all you need to do at this point is get your y coordinates. And if we go back to the graph, you can see that this right here is your first quarter, and it's going to be at 0. So you're on the x-axis. Then the midway, or the halfway point, you're going to be at +1 for the y-coordinate. And then for the 3/4 of the way, you're going to have a y-coordinate of 2. So it's going to be 0, 1, and then 2. Now, where is that coming from? Well, basically, you just have this +1 here. That's the only thing you're doing in terms of a vertical transformation. This right here is just a 1, if you want to write it. So basically, all you have to do is take your normal y values, which you get -1, 0, and 1, and just move them up by 1. So in other words, instead of -1, you get 0. Instead of 0, you get 1. And instead of 1, you get 2. This is going to be 0. This is going to be +1. And then this is going to be +2. Again, that's coming from those basic points from the tangent graph. So negative pi over 4 comma -1, your y-coordinate of -1, you add 1, you get to 0. And then your halfway point is 0, 0. Your y-coordinate of 0, you add 1, you get to 1. Then your pi over 4, comma 1, you take that y-coordinate of 1, you add 1, you get to 2. So those are your points for the quarter, half, and 3/4. So you can have 2 pi, comma 0. Let me label that. So this right here is 2 pi, comma 0. Then this one right here is 5 pi over 2, comma 1. So let me label that one. This one is 5 pi over 2, comma 1. And then this one is 3 pi, comma 2. So this one is going to be 3 pi, comma 2. Now, in terms of continuing this graph to the left or to the right, remember that for these points, you're always going to have the same y value. So this one, the first quarter point, you're always going to have a y value of 0. For the halfway, you're always going to have a y-coordinate of 1. For the 3/4 way, you're always going to have a y-coordinate of 2. So that's not going to change. The only thing that's going to change is the x value. And the way you can do this is you can just constantly add if you're going to the right or subtract if you're going to the left quarter periods. That's all you really need to do to find your additional points in your additional vertical asymptotes. Okay, so one more time I'll do this with transformations only. I know a lot of people want to see this because you don't get a chance to really practice this in the book because they don't cover it in most cases. So again, when I think about this, I can put a 1 right here. So really, in terms of a stretch or compression vertically, there's none. Right? So basically you have 1 times the tangent of whatever this is, and then +1. So there's no vertical stretch or compression. This is just a 1. But you do have this +1 on the outside here, which is giving me a shift up by 1 unit. So in terms of the vertical transformations, I know that I'm just going up by 1. Again, if you want to take these right here, and let's slide this down, and compare them to the original points from y equals the tangent of x, let me do this like this. You have -pi over 4, comma -1. you have 0, 0, and then you have pi over 4, 1. Well, again, all I'm doing is I'm just adding 1 to each y value. So -1 goes to 0. 0 goes to 1, 1 goes to 2. So we did that already, but basically that's all we're doing for the vertical transformations. Okay, let me put this right here. And now let's talk about the horizontal. Again, this is the one that's a little bit more confusing. And basically now we have the case where we have this 1/2 here. So remember, if it's between 0 and 1, now you're getting a horizontal stretch. Again, it's always the opposite of what you think. How do you undo multiplication by 1/2 or dividing by 2 if you want to think about it that way? Well, you need to multiply by 2. So the first step here, so step number 1, you're going to multiply by 2. This is going to be horizontally stretched by a factor of 2. And remember, this is going to be what you do first. Then this part right here, this is minus 5 pi over 2. So this is going to be done second. Again, it's the reverse of what you think. So since it's minus 5 pi over 2, I've got to add 5 pi over 2. So I want to shift to the right by 5 pi over 2. So let me put for number 2, this is going to be add 5 pi over 2. So again, if you always remember that things on the inside are the reverse. So basically this is 1/2. So to undo that, I need to multiply by 2. This on the inside is minus 5 pi over 2. To undo that, I need to add 5 pi over 2. And then you even go in the reverse order. So you reverse the order of operations. Normally you do what's inside of parentheses first, and then you would multiply second. You reverse that order. So you would do this one first, you do the multiplication first, and then you do this part right here, what's inside the parentheses second. So you have to keep everything straight with the horizontal transformations. I know it gets super confusing. So if this is not something that's straight in your mind, I would just go with the other procedure. You could start off with the vertical asymptotes. So just start with your x equals negative pi over 2 and x equals, you could do pi over 2 like this. So these are your vertical asymptotes when you think about the standard y equals tangent of x that you start with. So basically I'm going to multiply by 2 first. So let's go negative pi over 2 times 2. That's going to give me negative pi. And then once I've done that, I want to add 5 pi over 2. So let me start now with negative pi like this, and I'm going to add 5 pi over 2. Well, let's write this as negative 2 pi over 2. And what is that going to give me? Negative 2 pi plus 5 pi, that's 3 pi, and then over the common denominator of 2. So this would go to x is equal to 3 pi over 2. Then for this one, again, you're going to multiply by 2 first. Pi over 2 times 2. Let me show this so nobody's lost. That would give you pi. And then you're going to add 5 pi over 2. So write this as 2 pi over 2. You add that together, you're going to get 7 pi over 2. So this right here is going to become x is equal to 7 pi over 2. Let me put and there. And again, if you go back and check, we found from the other method that x is equal to 3 pi over 2 and x is equal to 7 pi over 2. Those are your vertical asymptotes. Now for the other x values, again, from that first quarter point from y equals tangent of x, you have an x value of negative pi over 4. So you take negative pi over 4, you multiply by 2 first. This would cancel. That gives you 2 down there. So this would be equal to negative pi over 2. And then from there, you're going to add 5 pi over 2. So this would give me 4 pi over 2. And 4 pi over 2 is 2 pi. Again, if you look here, for the first quarter point, you have an x coordinate of 2 pi. Again, we already figured out that the y coordinate was 0. Now for the next one, you have an x coordinate of 0. So you multiply that by 2. I don't even need to show that. That's still 0. And then you add 5 pi over 2. That's going to give you 5 pi over 2. So see, our x coordinate here is 5 pi over 2 for the midway point. So we just need the last one. So you have pi over 4 for that 3/4 of the way point for the x value. And again, I'm just going to multiply by 2. So this would cancel, give me 2 down there. So now I have pi over 2. And then once I've done that, I'm going to add 5 pi over 2. And this becomes 6 pi over 2, which is 3 pi. So again, you come over here and confirm with what we already did. For the 3/4 point, you're going to get 3 pi for the x value. So that's an alternative approach if you just want to use graphing transformations. As I told you in the last example, I know a lot of students struggle with it, particularly with the horizontal transformations, because everything is the reverse, or you could say counterintuitive to what you think. All right, let's talk about the cotangent function now. So most of you know that the cotangent of x is equal to the cosine of x over the sine of x. So again, just like we saw with our tangent function, the period is pi. You could take this point right here, which is pi over 4, and the cotangent value would be 1. You're dividing square root of 2 over 2 by square root of 2 over 2. This is your cosine value. This is your sine value. The same non-zero number divided by itself would be 1. If you swing around by pi, so if you add pi, and you go to this 5 pi over 4, which is right here, again, you're dividing the same non-zero number by itself. Here you have a negative square root of 2 over 2, and here you have a negative square root of 2 over 2, so you're still going to get 1. And the same thing would be true if you looked at, let's say, 3 pi over 4, and then you looked at 7 pi over 4. Well, here, the cotangent value is negative 1 because you're dividing opposites. So if you swing around, you're going to see the cotangent value is negative 1 there as well at 7 pi over 4. So the period here is going to be pi, again, just like with tangent. When we think about the fact that cosine of x is now in the numerator, well, anywhere where the cosine value is 0, so again, we know that's at pi over 2, 3 pi over 2, 5 pi over 2, or you could go negative pi over 2, negative 3 pi over 2, basically odd multiples of pi over 2, or you can say pi over 2 plus pi n, where n is any integer. That's going to be where the x-intercepts are now. So basically, that's where this is going to be 0, and this will not be 0. So 0 divided by something that's not 0 will give you 0. Then in terms of where it's going to be undefined, well, that's going to be where the sine values are 0, because again, that gives you division by 0. So that's going to be right here at 0, then at pi, then at 2 pi, 3 pi, or you could have negative pi, negative 2 pi. So basically you would say pi n, where n is any integer. Now I have a few basic points here. So just like we saw before. So we have at 0, this guy's undefined. Again, because your sine value is 0. Then at pi over 6, you're going to get square root of 3. At pi over 4, you're going to get 1. At pi over 3, you're going to get square root of 3 over 3. At pi over 2, you're going to get 0. At 2 pi over 3, you're going to get negative square root of 3 over 3. At 3 pi over 4, you're going to get negative 1. At 5 pi over 6, you're going to get negative square root of 3. And then at pi, you're going to get undefined. So we're going to graph this over the interval from 0 to pi, with both of those being excluded, because again, at 0, it's undefined. And at pi, it's undefined. So again, we're going to get vertical asymptotes at those values. All right, let's take a look at a basic sketch of y equals the cotangent of x. Just using these points right here. Again, when you first do the graph of this, you're just going to work from 0 to pi, with both being excluded. So you can see that at an x value of 0, the y value is undefined. Because if you have cotangent of 0, you have the cosine of 0, which is 1, over the sine of 0, which is 0, and 1 divided by 0 is undefined. So that's why you get undefined. Again, as this guy approaches an x value of 0, so coming from the right, as we do this, this guy's going to increase without bound. So it's going to approach positive infinity. Then similarly, for an x value of pi, again, the cosine of pi is negative 1, and the sine of pi is 0. So if I say I want the cotangent of pi, you're setting up the fraction negative 1 over 0, that's going to be undefined. So as your x value approaches pi, coming from the left. So coming from the left, going this way, this is going to decrease without bound. We're going to approach negative infinity. Now, in terms of this stuff in between, you have pi over 6, comma square root of 3. So here's your pi over 6 for the x value. This would be square root of 3 for the y value. So this point right here is pi over 6, comma square root of 3. Then you have your pi over 4, comma 1. So this is one that you want to memorize. That's going to be your first quarter point. We're going to use that. Then you have your pi over 3, comma square root of 3 over 3. So it's going to be this guy right there. Then you have your pi over 2, comma 0. So this is your halfway point. So you need to memorize that one. Then you have your 2 pi over 3, comma negative square root of 3 over 3. So that's this point right here. Then you have your 3 pi over 4, comma negative 1. So that's going to be this point right there. That's going to be 3/4 of the way through. So that's one that you need to memorize. And then lastly, you have this 5 pi over 6, comma negative square root of 3. So that guy right there. So that's your basic points. Usually you just put this point, and this point. You make a vertical asymptote here. You don't need to make one here. You can if you want, but typically you leave that off because this is the y-axis, so you don't draw anything. And basically you just draw this to where it approaches the y-axis and doesn't touch it. And this guy's going to approach this vertical asymptote, which is x equals pi, but not touch it. So that's all you really need to do. So just like with the graph for y equals the tangent of x, when you expand this to the right or to the left, all you're doing is just copying what you previously did. In other words, we graphed this right here, so from 0 to pi with both being excluded, but basically the same thing's going to happen from pi to 2 pi, 2 pi to 3 pi, or if you went this way, you can say from negative pi to 0, you could say from negative 2 pi to negative pi, so on and so forth. So you're going to have a vertical asymptote, you're going to have 3 points, vertical asymptote. So it's just that pattern over and over and over again. And these 3 points, again, the benefit to these guys right here is that basically all you need to know is what is the vertical asymptote here and what is the vertical asymptote here. So I'll show you how to get that in a moment. Once you have this one right here on the left, in this case it would be 0, you just add a quarter period. Well, a quarter of the normal period, the period for cotangent is pi, so a quarter of that is pi over 4. So I know the x value right here is pi over 4. And of course, the y value is 1. We can see that. Then this one right here, again, you just add a quarter period. So pi over 4 plus pi over 4, that's 2 pi over 4, or pi over 2, and the y value is 0. Then for this one, again, I'm just adding a quarter period. Let me make that arrow better. So if you have, let's go 2 pi over 4, so we have a common denominator, plus pi over 4, that's going to be 3 pi over 4, comma, negative 1 for the y value. So the y values are things that you want to memorize because typically you're going to do this with graphing transformations. So if you know those y values, it's going to save you a lot of time. You can always plug in if you want to, but I find that to be a very tedious process. For the x values, again, all you're going to have to do is find the vertical asymptotes, figure out the period and the quarter period, and then just go through the process of adding quarter periods to get to the next x value. So I start here, add a quarter period, I get to this x value, add a quarter period, add a quarter period, add an asymptote. Add a quarter period, add a quarter period, add a quarter period, add an asymptote, so on and so forth. All right, let's talk a little bit about the cotangent function in general. So the domain contains all real numbers except for pi n, where n is any integer. So 0, pi, 2 pi, 3 pi, or even negative pi, negative 2 pi. That's where the sine value is 0, and again, division by 0 is undefined. So f of x equals cotangent of x is discontinuous at pi n, where n is any integer, and the graph contains vertical asymptotes at those values. The x-intercepts, so again, this is where the numerator would be 0, and the denominator is not 0, so these are of the form x equals pi over 2. Remember that cosine of pi over 2 is 0, and then plus pi n, where n is any integer. The x-intercept occurs at half of the way between consecutive vertical asymptotes. So if we use that basic y equals cotangent of x over the interval from 0 to pi, both being excluded, this is going to happen at pi over 2 comma 0. So you want to memorize that point. Then the point on the graph 1/4 of the way between consecutive vertical asymptotes has a y-coordinate of 1. So we saw that already. So if you're using y equals cotangent of x over the interval from 0 to pi, with both being excluded, well, you're going to have pi over 4 comma 1. Lastly, the point on the graph 3/4 of the way between consecutive vertical asymptotes has a y-coordinate of negative 1. Again, using y equals cotangent of x over the interval from 0 to pi, with both being excluded, you saw that we had 3 pi over 4 comma negative 1. So again, the period is pi. There are no minimum or maximum values. The range is from negative infinity to positive infinity, and the graph has no amplitude. So the graph is symmetric with respect to the origin. So if you did cotangent of negative x, it's equal to the negative of cotangent of x for all x in the domain. So f of x equals the cotangent of x is an odd function. So just like we saw with tangent, I gave you a little model you can use. It's not going to fit perfectly with every scenario, but we can just adjust it. So we have y equals a cotangent of bx minus c, where b is greater than 0. Again, if b is negative, which you'll see in the future, you can rewrite it using identities. If you need the period, you can just use absolute value bars. It's really not that big of a deal. It won't cause that much concern. So what we would do is say that you're going to take this bx minus c like this, and you're going to find an interval over which you're going to graph it by saying it's greater than 0 and less than pi. And that's coming from the fact that if you have y equals the cotangent of x, well, we said that we're going to go x is greater than 0 and less than pi. So again, all you're doing is you're taking this argument right here, which is the bx minus c, and you're just putting it in that place right there, and you're going to solve for x. That's all you have to do. So basically, once you've done that, you're going to find these two vertical asymptotes. So you could do it as an equation. Bx minus c is equal to 0. So that's for this one. And then bx minus c is equal to pi for this one. And then once you have that, just like with the tangent function, you can figure out what the period is. So it's just going to be pi over b. Let me write that out. So the period is just pi over b. So whatever that is, that coefficient of x. If you end up factoring that out, so if you have something like y equals a cotangent of, let's say we pull the b out because we want to use graphing transformations. Let me move this up so it fits. So then inside you would have x minus c over b, like that. Well, the period is still pi over b. So in this form, it's the coefficient of x. In this form, it's outside of the parentheses. So just keep that in mind. Now, once you have that period, you can just figure out the quarter period. So the quarter period, again, that is just pi over 4b. So just take this and multiply it by 1/4. And once you have that, you take the x value here, you add a quarter period, you're going to get your x value here. So the y-coordinate would just be given by a in this form. But again, if you have a shift, you have to consider that as well. You do this multiplication here first by your typical y-coordinate for y equals cotangent of x, which in that case is going to be positive 1. And then once you've done that, you need to apply your shift either up or down. This 1/4 point, the y-coordinate is a because, again, 1 times a would be a. Then at the halfway point, the x-intercept, well, again, I could just add a quarter period to get the x value there. And then for the y value, in this form, it's just going to be 0. But again, if you have a shift up or down, you have to consider that. And then you add another quarter period to get the x value. And then you're going to have your 3/4 point and the y-coordinate is now negative a. Because normally, if you have y equals cotangent of x, 3/4 of the way through, you have that 3 pi over 4 comma negative 1. So if you take that negative 1 and you multiply by a, you get negative a. That's where that's coming from. So just keep this in mind as a general model. And with that being said, let's just go ahead and look at an example. All right, let's take a look at an example now with cotangent. So we have f of x equals the cotangent of x over 2 plus pi over 3. To start things off, I'm just going to go x over 2 plus pi over 3. So that's going to be the argument for the cotangent function there, this guy. And basically, you're going to say that this is greater than 0 and less than pi. So I'm going to get rid of these fractions here. You have a denominator of 2 and a denominator of 3. So what I would do is just multiply both sides by the LCD, which would be 6. So 0 times 6 would still be 0. Let me just show it for right now. Multiply this by 6, multiply this by 6. Let me slide this over here, and then multiply this by 6. Let me drop down a little bit. So as I just said, 0 times 6 is still 0. This is less than 6 divided by 2 would be 3, and 3 times x is 3x, and then plus 6 divided by 3 is 2. 2 times pi is 2 pi. And then this is less than 6 times pi is 6 pi. If you want to isolate x in the middle, then what you're going to do is subtract 2 pi away from each part here. Let me just put minus 2 pi here. And so this is going to cancel. We're going to have our 3x in the middle, and this is greater than negative 2 pi. And it's less than 6 pi minus 2 pi would be 4 pi. As a final step here, let me divide each part by 3 just to finish things up. So this is going to cancel. And what you're going to have is that x is greater than negative 2 pi over 3 and less than 4 pi over 3. Let me come down here and just paste this in, and I'll put a little border, and I'm going to say that's my consecutive vertical asymptotes. So vertical asymptotes, you're going to have x is equal to, you have this negative 2 pi over 3, and then let me write that better there. And let me fix this 3 here. We're going to say x is equal to 4 pi over 3. Let me show you this graphically first. So coming down to the graph, you see that you have a vertical asymptote here, and this is our x equals negative 2 pi over 3. And then you have a vertical asymptote here. This is going to be our x equals 4 pi over 3. So that we know, we need to figure out this point, and this point. So let's go back up. So what you want to do is figure out what is the period. And for this, again, let's go up here. When you look at this, you have x over 2. So you can think about that as 1/2 times x. So the standard period is pi. Again, all you're going to do is go pi over 1 divided by 1/2, or times the reciprocal of that, which is 2 over 1. So this is 2 pi for the period. And let's write the period as 2 pi. And then the quarter period, this is going to be 2 pi over 4, which is pi over 2. So again, all you have to do at this point is just go through and say, well, I'm going to go negative 2 pi over 3 plus pi over 2. So just starting at that leftmost vertical asymptote that we found. And you need a common denominator here. So let me actually write this. I'm going to multiply by 3 over 3. And I'm going to put this as, let me scooch this down a little bit so we have some room. This would be 3 pi over 6. So I have a common denominator. And this guy right here, I'm going to write as negative 2 pi over 3 times 2 over 2. So this would be negative 4 pi over 6. So I'm just going to start with that. So negative 4 pi over 6, and then plus the quarter period. So that's 3 pi over 6. That's going to give you negative pi over 6. So let me write this on another page. For this one, your first quarter point, you're going to have negative pi over 6. We'll get the y values in a second. I think all of you can see that there's no vertical transformations that are applied. So you could just put 1 now if you want, but I'll just do that separately. So then we have the 1/2, and then we have the 3/4. And let's go up and get those. So I'm going to start now with the negative pi over 6. And I'm just going to keep adding quarter periods. So I'm going to add 3 pi over 6. So this gives me 2 pi over 6. 3 pi minus pi, that's 2 pi. And 2 pi over 6, you can write that as pi over 3. Let's come down here and say this is pi over 3. And then let's do that one more time. So we would want to do 2 pi over 6. So 2 pi over 6 plus the quarter period. We'll write that as 3 pi over 6. So that gives me 5 pi over 6. Let's come down and put 5 pi over 6. Now, for the y values here, again, when you look at these points, you see the y value here is 1, the y value here is 0, and the y value here is negative 1. That perfectly matches what we see with y equals the cotangent of x. And the reason for that is you don't have any vertical transformations here. This you could really put as a 1, so there's no vertical stretch or compression. And out here, you don't have anything. So you could put +0 to make that clear. There's no shift up or down. So you would match those y values perfectly. So for the first quarter point, you have a y value of 1. For the midway point, you have a y value of 0. And for the 3/4 of the way point, you have a y value of -1. So let's put 1 here. Let's put 0 here. And then -1 here. So we're ready to go in terms of labeling those points. You would have -pi/6, 1. So that's going to be this first point right here. So this is -pi/6, 1. That 6 could be a lot better. Then we have pi/3, 0. So this one right here, let's say that's pi/3, 0. And then this one, the 3/4 of the way, it's 5pi/6, -1. So this one, we'll say that this is 5pi/6. Let me make that 6 a lot better there. And then -1. So those are your 3 key points. Again, if you want to go to the right or to the left, you just keep adding quarter periods. So in other words, if I take this 5pi/6 and I add a quarter period, I'm going to be at 4pi/3. And you could just keep doing that to get the next point, the next point, the next point, vertical asymptote. The next point, the next point, the next point, vertical asymptote. The y values are always going to be the same. In other words, for the first quarter point, you're always going to have a y value of 1. For the halfway point or the midway point, you're always going to have a y value of 0. And then for the 3/4 of the way point, you're always going to have a y value of -1. All right, let's take a look at another one. So here we have f of x equals 1/2, and then cotangent of, we have 2x plus 2pi/3, and then +2. All right, so again, I'm just going to take the inside part here, so the argument for the cotangent function, and I'm going to start by saying 2x plus 2pi/3 is greater than 0, and it's less than pi. So we'll solve this first. And so let me slide down here just a little bit. I would get rid of this denominator of 3. So just multiply everything by 3. So you would have 0 times 3. Let me show this. So 0 times 3 is less than 2x times 3 plus 2pi/3 times 3. And this is going to be less than pi times 3. So 0 times anything is 0. So this is still 0. This is less than. 2x times 3 is 6x. And then plus, these 3's would cancel. So you have 2pi. So which is less than 3 times pi is 3pi. So at this point, I'm going to subtract 2pi away from each part. Let me write that like that. And so this is going to cancel. You're going to have 6x in the middle. So this is greater than, you're going to have -2pi. And less than 3pi minus 2pi is pi. To finish things up, let's divide everything by 6. And so that's going to give me this canceling in the middle. So x is greater than, if you think about 2 and 6, well, 2 divided by 2 is 1, and 6 divided by 2 is 3. So let's say this is -pi/3, and it's less than pi/6. So let's grab this. Okay, let me put that in there like that. So again, your 2 consecutive vertical asymptotes. So vertical asymptotes, you're going to have x is equal to -pi/3, and then you're going to have x is equal to pi/6. All right, so this one's a little bit busy. So again, I've given you a link on Desmos if you want to click that to get more detail. This is your vertical asymptote, which is going to be x equals -pi/3. So that guy right there. Then this is the other one. So this is the vertical asymptote. It's x equals pi/6. So we're going to be finding these 3 points right here. So let's go back to right here. If you want your period, again, it's pi, which is your standard period, divided by 2, the coefficient of x. So it would be pi/2. So let me write that the period is going to be pi/2. And then your quarter period, so this is pi/2 times 1/4. So that's pi/8. So again, all you have to do is take this -pi/3, and you're going to add a quarter period. So you're going to add pi/8. Now again, you need a common denominator. So let's just go ahead and right now multiply this by 3/3, just so that we're not struggling the whole time to get common denominators. So this right here would give me 3pi/24. Okay, so let me adjust this. I'm going to write -pi/3 as -8pi/24, and then I'm going to add 3pi/24. So then for the first quarter point, the x value would be -8pi plus 3pi. That's -5pi, and this is over 24. And let me put, for the first quarter point, you want -5pi/24. Okay, so we're going to have halfway and then 3/4. We're going to figure those out right now. So let me take this, -5pi/24, and all I'm going to do is add a quarter period. So let me rewrite that. It didn't take it with it. So plus 3pi/24. So -5pi plus 3pi, that's going to be -2pi/24. over 24. So if you think about that, you can simplify. 24 divided by 2 is 12, and 2 divided by 2 is 1. So this would be negative pi over 12. So this is negative pi over 12. And let me get rid of that. And we only have one more to do. So let me move this over. So let me add 3 pi over 24 one more time. And so negative 2 pi plus 3 pi, that's going to be pi. And this is over 24. So this would be pi over 24. Okay, in terms of the y values, you do have to do a little bit of work here because you do have two transformations that are vertical. So let me start off with these basic points here. So on the y equals cotangent of x, you're going to have your pi over 4, comma 1. Then you're going to have pi over 2, comma 0. And then you're going to have 3 pi over 4, comma negative 1. So we're going to think about how we're going to transform here. Again, in terms of vertical, you have this guy that's done first. This is a multiplication by a half. So that's giving me, you could say, a vertical compression by a factor of 2. Or again, a lot of people like to say it as a vertical shrink by a factor of a half. It's just understanding that you're either going to divide each y value by 2 or you're going to multiply by 1/2. It's the same thing either way. It's just a matter of how you want to say it. This right here, this plus 2, that's going to shift me up by 2 units. So this is done first, this is done second. So the order does matter here. So let me write this out. We're going to, for part 1, multiply by 1/2, or again, you could divide by 2 if you want. And then for part 2, we're going to add 2. So again, this is a vertical compression by a factor of 2. Then you're going to add 2, that's shifting me up by 2 units. Okay, so we're first going to multiply 1 by a half. So 1 times 1/2 would be 1/2. Then I'm going to add 2. So you would have 1/2 plus, for 2, you could write that as 4 over 2. So this would be 5/2. So this is 5/2. All right, for this one right here, you have 0 times a half. That's still 0. Then you add 2. That's going to be 2. And then for this one, you have negative 1 times a half. That's negative 1/2. And then you add 2. So let's add 4 over 2. So this would be 3/2. So that's basically it. Just a matter of understanding those graphing transformations. Again, if you get confused by that, you can always plug in. So you could always take negative 5 pi over 24, plug into the original function, you'll get 5/2. You could plug in negative pi over 12, you'll get 2. You could plug in pi over 24, you'll get 3/2. All right, let me get rid of this. And let's just label things and we'll be done. So for this one right here, you have negative 5 pi over 24, comma 5/2. So that's going to be this one right here. So this is negative 5 pi over 24, comma 5/2. And if you look at this, it's hard to see, but this notch right here is 2. So this notch right here would be 2.5 because this notch right here is 3. And then if you look at this one right here, that's going to be negative pi over 12, comma 2. So that is negative pi over 12, comma 2. And again, this notch right here is 2. It's covered up by that point. And then if you look at this one right here, we're going to have pi over 24, comma 3/2. So this is pi over 24, comma 3/2. And again, this notch right here is 1. This notch is 2. So this is halfway. So that's 1.5 or 3/2 in terms of your y value. So you can see that does match up. Again, if you want to click the link on Desmos, you can see I've labeled all of these points for you so you can go through there and you can get some additional practice by basically just adding quarter periods to this guy. So to the x values here, you'll get your vertical asymptote, and then you're going to get the x coordinates for this guy, this guy, this guy, vertical asymptote, this guy, this guy, this guy, vertical asymptote, so on and so forth. You know the y values are always going to be the same. So for the first quarter point, you're going to have 5/2. Then for the midway point, you're going to have 2. Then for the 3/4 of the way point, you're going to have 3/2, so on and so forth. So if you want to play around with it and get some additional points going on your graph, going to the right and to the left, it'll be good to get some practice. In this lesson, we want to learn about graphing secant and cosecant. All right, before we get started with the lesson, I want to remind you that when you're in this section and you're graphing trigonometric functions, we want to understand the concept. So how could I graph the function if I wanted to? But generally speaking, if we want to get a perfect graph, we're going to use graphing software, and that's something we're going to rely on as we get out of this chapter. So don't worry too much about trying to make some perfect graph. Just do the best that you can. So when we look at this, we're going to start out by saying that in our lesson on cosine and sine, we learned that the period was 2 pi. When we think about something like the secant function, so the secant of x, this is equal to 1 over the cosine of x. So what would the period for the secant function be? Well, it's going to be 2 pi as well. The secant of x is equal to the secant of, you have this x plus 2 pi n, where x is a member of the domain and n is any integer. In other words, if I was to come to the unit circle, and let's say that I took the secant of, let's just do pi over 3, that's an easy one. So the secant of pi over 3, this would be equal to, by definition, 1 over the cosine of pi over 3. And so the cosine value for this pi over 3, again, you just look at the x-coordinate, so that's 1/2. So this would be equal to 1 over 1/2, which would be 2. If you added integer multiples of 2 pi to this angle pi over 3, so in other words, you could add 2 pi to it, 4 pi, 6 pi, or you could subtract away 2 pi, subtract away 4 pi, something like that, you're going to end up with a coterminal angle. So you're going to have the same cosine value and also the same secant value. So just to keep it simple, let's say we have the secant of, let's go pi over 3 plus 2 pi. And I would write that 2 pi as 6 pi over 3. So we have a common denominator. So 6 pi over 3. So this would be the secant of 7 pi over 3. And of course, that's going to be coterminal with pi over 3. So we know that the cosine value would be the same. So this is 1 over the cosine of 7 pi over 3, which would be equal to, again, 1 over this 1/2, which would be 2. So the period for secant is going to be 2 pi. Now let's talk about cosecant. So using a similar thought process, when we think about the cosecant of x, this is equal to 1 over the sine of x. And of course, the period of the sine function is 2 pi, so the period for the cosecant function would be 2 pi as well. So the cosecant of x is equal to the cosecant of x plus 2 pi n, where x is a member of the domain and n is any integer. All right, so we're going to start out by looking at the secant function, and we're going to do that with a table of values, and we're going to look at this over one period. So y equals the secant of x. We're going to say where x is greater than or equal to negative pi and less than or equal to pi. Now, we're not going to use this table of values approach when we graph secant in general. We'll have a different procedure for that. We're just using this to get some key points here. Now, with the other graphs for sine and cosine, and then also with tangent and cotangent, there were points that you really needed to memorize. You're not going to do that here because you're going to end up using the cosine function as a guide, and we'll get to that later on. For right now, I'm just going to focus on some things that we want to know. And so the first thing would be that you have a vertical asymptote here at negative pi over 2, and then also at pi over 2. So we want to think about where that comes from. Remember that the secant function, so the secant of x, is equal to 1 over the cosine of x. So just like we saw with the tangent function, you have your cosine function in the denominator there. So wherever the cosine values are 0, you're going to get division by 0, which is undefined, and that's giving you these vertical asymptotes. So that's going to happen at odd multiples of pi over 2. So negative pi over 2, 3 pi over 2, 5 pi over 2, so on and so forth. Now, another thing I want to call your attention to is that when you look at the behavior of this graph, so let's say as this guy right here goes from an x value of 0 to an x value of pi over 2. Now, it's not actually going to get to an x value of pi over 2, but you want to think about what's happening as it approaches an x value of pi over 2 coming from the left. So we would think about something like, let's say, secant of, let's just do pi over 3 again. That's an easy one. This is equal to 1 over the cosine of pi over 3, which is 1 over, again, the cosine of pi over 3 is 1/2. So notice that this value right here of 1, when I divide by 1/2, I get something bigger, I get 2. When you take 1 and you divide by something between 0 and 1, you're going to get something that's larger than 1. For example, if I did, let's say 1 divided by 1/10, I would get 10. Or let's say as another example, I did 1 divided by 1 over 100, well, that would be 100. So what's going to happen is, as the x value here gets closer and closer to pi over 2, the cosine value gets closer and closer to 0. So you can get as close to 0 as you'd like, but you can't actually touch it. So what's happening is the value is going to get really large for secant because you have that 1 divided by that number that's really, really close to 0. So this guy right here is going to increase without bound, or as they say, approach positive infinity. So let me get rid of this. We also want to think about the other side of that. So at pi, so the secant of pi is equal to 1 over the cosine of pi. So we know that the cosine of pi is negative 1. 1 over negative 1 would be negative 1. So here, this point would be pi, comma, negative 1. Now, what happens as we approach pi over 2 coming from the right? In other words, what's going on right here? And you'd see that we're decreasing without bound, so we're approaching negative infinity. Basically, what's happening is, if you think about something like, let's say, the secant of 2 pi over 3, to make it simple. So there's a pi over 3 reference angle. So we know that we're in quadrant 2. Cosine is negative. So this would be 1 over the cosine of 2 pi over 3. And this equals 1 over, now you'd have negative 1/2. And so this would be negative 2. So it's the same thing here. If you look at that point, it's going to be right there. So this would be your point, which would be 2 pi over 3, comma, negative 2. Again, as this x value gets closer and closer to pi over 2, again, coming from the right now, the cosine value is getting closer and closer to 0, but it's on the other side of 0. So it's going to be something between 0 and negative 1 now. So this guy is now going to approach negative infinity. So that's just something you really need to understand about the behavior of this graph. That's why you have this going this way, that's why you have this going this way, and that's why you have this shape right here. So once you understand that, it's basically good to go in terms of why the graph looks the way that it does. And now what I want to do is just erase some things and give ourselves a little clean slate here. And I want to go through some of these basic points. So first off, you should know this point right here, which is 0, 1. That's one that's going to be on the graph of your cosine function and your secant function. Then this one right here, this is your pi, comma, negative 1. Again, that's going to be on both. And then this one right here, that's going to be negative pi, comma, negative 1. Now, in terms of these other points, if you want to go through them in more detail, I left you a link on Desmos. So you can stop the video here, click that link, and you can look at all these points and think about where they're coming from. I'll just read through them real quick. If you have plus or minus pi over 2, again, that's where we're going to be undefined because the cosine value is 0. You have 0, 1, so that's this point right here. Then this plus or minus pi over 6, you get 2 times square root of 3 over 3. Let me actually show you that real quick so these other guys make sense. Coming back to the unit circle, again, if I asked you for the secant of pi over 6, or I asked you for the secant of negative pi over 6, you're going to get the same thing because, again, when you look at pi over 6, the cosine value is square root of 3 over 2. When I look at negative pi over 6, again, that's rotating clockwise. So that's coterminal with 11 pi over 6. Let me write out that this is negative pi over 6 here. So the cosine value is, again, square root of 3 over 2. So whether I take the secant of pi over 6 or the secant of negative pi over 6, again, I'm going to be in either quadrant 1 or quadrant 4, where cosine and secant are positive, and I have the same reference angle, so I'm going to get the same result. Let me just do this one real quick. You can get rid of this one. I'll just show you this real quick. So this would be equal to 1 over the cosine of pi over 6. And of course, this is 1 over the square root of 3 over 2. And so this would be equal to, you're just going to flip this and say this is 2 over the square root of 3, and then multiply it by the square root of 3 over the square root of 3 to rationalize the denominator. So you get 2 times the square root of 3 over 3. And again, this would be for pi over 6 or negative pi over 6. So coming back down, again, plus or minus pi over 6, you're going to get 2 times square root of 3 over 3. Plus or minus pi over 4, you're going to get square root of 2. Plus or minus pi over 3, you're going to get 2. Plus or minus 2 pi over 3, you're going to get negative 2. Plus or minus 3 pi over 4, you're going to get negative square root of 2. And then plus or minus 5 pi over 6, you're going to get negative 2 times square root of 3 over 3. And then plus or minus pi, you're going to get negative 1. You can look at that link again on Desmos if you want to go through those points. Again, we're not going to focus too much on these points. We're going to use the cosine function as a guide, so don't worry about this too much. Okay, now let's actually get into the procedure. So how do you sketch the graph of the secant function where you're going to use the cosine function as a guide? So you know how to graph the cosine function at this point. If you do it over one cycle, you would do this part right here. And I'm just going to trace over this real quick. So from 0 to 2 pi. So this is what your basic cosine function looks like. And we've graphed that a million times at this point. So you would graph that guy right there. And then what you're going to notice is that you have a shared point here. So at 0, 1, and then also here at pi, negative 1, and then also at 2 pi, 1. And I'll talk about how those come into play in a moment. But you'll notice that where you have an x-intercept, so that's right here at pi over 2 and right here at 3 pi over 2, because again, when you have the cosine of pi over 2, you get 0. When you have the cosine of 3 pi over 2, you get 0. So those are x-intercepts, and therefore, that's going to make your secant function undefined because you can't divide by 0. So you're going to get those vertical asymptotes at those values. So this is what you want to focus on here. Now, that's going to change a little bit when we get to shifting the graph up or down, and I'll explain how to compensate for that. For right now, we're just going to learn it this way. So when you think about this all together, just going over the whole graph that we have here, you would say that wherever the y value is 1, you're going to have a shared point. So that's going to happen at an x value of 0, and then an x value of 2 pi, and then 4 pi, 6 pi, 8 pi, so on and so forth. And then going this way, you'd have negative 2 pi, negative 4 pi, negative 6 pi, so on and so forth. So you could say at 2 pi n, where n is an integer, the y value would be 1, and you're going to have a shared point between your secant graph and your cosine graph. Then similarly, when you think about having a y value of negative 1, again, that's going to have a shared point. So something like, let's say, pi, negative 1. And if you add 2 pi to that, you'd have 3 pi, negative 1. If you subtracted away 2 pi from this pi here, you'd have negative pi and then negative 1. And then here's your negative 3 pi, negative 1. So this would be at pi plus 2 pi n, where n is any integer. So 5 pi, negative 1 would be there, 7 pi, negative 1 would be there, something like negative 5 pi, negative 1 would be there, so on and so forth. The idea here is you want to think about that as being shared points, because when you see that there's a shared point, you're going to what we call interchange the hills and the valleys. So what I mean by that is when you think about the graph of cosine, you know that you have a maximum point anywhere where the y value is 1 and a minimum point anywhere where the y value is -1 because the range of cosine is from -1 to +1 with both being included. So here you'd have a maximum point and then again here and then here. So when you think about it, this maximum point right here corresponds to what we call a local minimum point on the graph of the secant function. So this right here is a hill and this right here is a valley. So the hills and the valleys are going to be interchanged. So this right here is a hill, this is a valley. Hill, valley. Then when we get down here, let me use a different color, you think about the fact that, okay, now when we look at our cosine graph, this is going to be a valley or a minimum, and then here this would be a local maximum or a hill. And then when you come here, it's the same thing. So this is a valley, this is a hill. Valley, and then this is a hill. You have a valley, and then this is a hill. So that's all you really need to memorize. The hills and the valleys will be interchanged. That's how pretty much every book says it, and that's how I remember it. Now, the last thing, again, like we talked about a moment ago, is how to get these vertical asymptotes. So without shifting the graph up or down, you're going to think about where are the x-intercepts for the guide function, the cosine function. Again, that's going to happen at odd multiples of pi over 2. So at this -5 pi over 2, -3 pi over 2, -pi over 2, pi over 2, 3 pi over 2, and then 5 pi over 2. So this would be a vertical asymptote here for your secant function. Again, you'd have one here, and then here, and then here, and then here, and then here. And again, this continues forever. So you would have 7 pi over 2, 9 pi over 2, so on and so forth. All right, let's just go through the characteristics of the secant curve. So the domain consists of all real numbers except odd multiples of pi over 2. Again, this is because at odd multiples of pi over 2, you're going to get a cosine value of 0, division by 0 is undefined. So f of x equals the secant of x is discontinuous at odd multiples of pi over 2. The graph contains vertical asymptotes at those values. There are no x-intercepts. You will only see those if you start shifting the graph up or down. And then the period is going to be 2 pi. So there are no minimum or maximum values. We saw that the range is from -infinity going up to -1 and including -1. And then the union width you have from 1 and including 1 out to +infinity. You will not see any y values between -1 and +1, again, because of the range of the cosine function, which is from -1 to +1, and the definition of the secant function, which is 1 over the cosine of x. Again, something we talked about earlier when we were describing the behavior of the graph. So the graph has no amplitude, again, because there are no minimum or maximum values, and the graph is symmetric with respect to the y-axis. So the secant of -x is equal to the secant of x for all x in the domain. So we can say f of x equals the secant of x. That is an even function, just like cosine. All right, so real quick, we have a graphing procedure, and you can write this down if you want. It's something you can just memorize if you don't want to write it down. It's not a big deal. So graphing variations of the secant function. The first thing you want to do is replace the secant with cosine and sketch the graph using a dashed curve. So cosine is used as a guide. Then you want to sketch the vertical asymptotes. So this is the one that you really might have trouble with, this step right here. And the reason for that is that if you get a vertical shift involved, then you're not going to look for the x-intercepts of the cosine function or the guide function. It's going to be moved around, and I'll show you that when we get to an example. The way I remember it is these occur at 1/4 of the way and 3/4 of the way through the cosine cycle. Again, just going back to this, here is the cosine graph if you look at it over one cycle. So if we look at it over one cycle, it looks like that. So at the start of the cycle, your x value is 0. When you get 1/4 of the way through, your x value is pi over 2, so you have an x-intercept. When you get to the middle, your x value is pi. 3/4 of the way through, your x value is 3 pi over 2, so you have an x-intercept, and then you finish up at 2 pi for the x value. So 0, pi over 2, pi, 3 pi over 2, and 2 pi. So just keep that in mind. When we look at these variations of this guy, we're going to use the same thought process. So 1/4 of the way through and 3/4 of the way through, that's where we're going to have our vertical asymptotes for the secant function. All right, then we have sketch the graph by drawing the U-shaped branches between consecutive vertical asymptotes. So you have that the hills and the valleys are interchanged. So all you're going to do is you're going to take those shared points, you're going to start there, you're going to make your U-shaped branches, and you're going to approach your asymptotes, but not touch them. Then we have optional here, use the period to find additional cycles to the left or the right as needed. And again, if you're self-studying, I would just do one period and call it a day. Usually if you're given an assignment, your teacher will say, hey, I want you to sketch it from this place to this place. So just follow that. Okay, let's take a look at an example now. So we have f of x equals 1/2 secant of 2x plus 5 pi over 6, and then plus 1. So instead of just going straight into replacing secant with cosine, let's just get some information. So let's just go ahead and say that we have f of x is equal to 1/2, and then the secant of, I'm going to factor out the 2. It just makes it easier to find the phase shift. So pull that out, you're going to have x plus, how do I undo multiplication by 2? I would divide by 2 or multiply by a half. So this would be 5 pi over 6 times a half, which is 5 pi over 12. And so when we look at it now, finding the phase shift is very easy. You just want to say, inside the parentheses here, how do I undo what's being done to x? We have this plus 5 pi over 12. To undo that, you want to subtract away 5 pi over 12. So for the phase shift, you could say minus 5 pi over 12, or most people will just say left 5 pi over 12. Now, in terms of the vertical shift, that's very straightforward. So you have this plus 1 here. So the vertical shift, that's just going to be up 1. Now, thinking about the period, so we'll need that. So what is the period for this guy? Again, the standard period is 2 pi when you're looking at either sine, cosine, secant, or cosecant. And we're just going to divide that by the number outside the parentheses here. If it's in unfactored form, it's the coefficient of x. So 2 pi over 2, which would be pi. And then for the quarter period, depending on the method you're going to use to find your points for the cosine function we're going to get in a minute, you would want to take this period, which is pi, and divide it by 4. So the quarter period is pi over 4. Now, let me put a little border here. I'm going to talk about the graphing transformations, and you can use this method if you want, or you can use a different method. It's really going to be up to you. So in terms of x, remember, this is the one that's really hard for students. That's why a lot of people just turn to the quarter period method, because this becomes a little bit challenging to remember. You need to undo what's being done to x. And so to undo something, you have to go in the reverse order. Think about writing a Word document or something like that. You hit Control Z. You're undoing the latest thing you did. You don't undo the first thing you did. So if you look at the order of operations here, again, you have parentheses here. And I know you could distribute that 2n, but we're not doing that here. So from the order of operations, we know we would work inside the parentheses first and then do the multiplication second. So if I write this out, now I have to go in the reverse order. So this would be 1 and this would be 2. And each thing has to be undone. So how do I undo multiplication by 2? I would divide by 2 or multiply by half. So you would multiply by 1/2. So that's giving me a horizontal shrink by a factor of a half. I know a lot of teachers will also say this as a horizontal compression by a factor of 2. Again, I don't want to get caught up on the terminology. A lot of people get confused by those two ways of saying the same thing. Just realize that you're having your x coordinate either divided by 2 or multiplied by half. Then the second thing is you want to undo this plus 5 pi over 12. Well, we want to subtract 5 pi over 12. Again, we saw that earlier when we did the phase shift. That's going to shift me to the left 5 pi over 12. Then when you think about the transformations for y, these are the ones that are very straightforward. You have this 1/2 here that's multiplying this guy. So the first thing is you would just follow that. So multiply by 1/2. And the second thing is you're adding 1. So you're going to add 1. Again, this is straightforward. It follows the order of operations. You multiply before you add. So with this one, you're getting you could say vertical shrink by a factor of a half, or you could say vertical compression by a factor of 2. Again, I know that confuses people when you have two different ways to say the same thing, but just realize you're taking the y coordinate and you're either dividing it by 2 or you're multiplying it by half, and then you're going to add 1. That's shifting me up by 1 unit. Okay, so coming to a new sheet here, I'm going to erase the secant and just put in cosine. So remember, we're going to graph this as a guide. So how do you graph this cosine function? Again, lots of ways to do it. You can use all graphing transformations. You can use no graphing transformations. It's really up to you. So I'm going to do both the quarter period method and all graphing transformations method. And then on the next ones, I'll just use the quarter period method because it's a little bit easier for students to understand. So when we think about using the quarter period method, you start off by thinking about your points for the basic cosine function. So y equals cosine of x. You have a point. You start off at the maximum, so 0, 1, and then you're going to go to your x-intercept. So this is pi over 2, 0, and then you're going to go to your minimum. So this would be at pi, -1. You go back to an x-intercept. So this is 3 pi over 2, 0, and then you're going to finish up at the maximum. So 2 pi, 1. So these are points you should have memorized at this point. And all we're going to do is think about, for the first x value here, you just use the phase shift. In other words, you have this 0 right here, and I'm going to think about what is the phase shift. So we know it's to the left by 5 pi over 12, or you could say I'm subtracting away 5 pi over 12. Again, I've got to undo what's being done to x there. So this x coordinate would be -5 pi over 12 right there. To get the additional x coordinates here, all you're going to do is you're going to take this value right here. Don't worry about these. This value right here, and you're going to keep adding quarter periods. So the quarter period, again, was pi over 4. You took your period, which is pi, divided by 4. Here I'm going to multiply this by 3 over 3, so we have a common denominator, so it's 3 pi over 12. So you're going to keep adding 3 pi over 12. Again, start here, negative 5 pi over 12 plus 3 pi over 12. That would give me negative 2 pi over 12. I know you could simplify that, but let's just hold off for a moment so we have a common denominator. So negative 2 pi over 12 plus 3 pi over 12, that would give me pi over 12. Then pi over 12 plus 3 pi over 12, that's 4 pi over 12. Again, don't simplify it yet. 4 pi over 12 plus 3 pi over 12, that's 7 pi over 12. Now this right here, this 4 pi over 12, you could write that as pi over 3. So this is pi over 3. And then negative 2 pi over 12, you could write that as negative pi over 6. So negative pi over 6. Let me make this better here. Before we go on, I want to show you that you can get the same values here just using those graphing transformations that we talked about a moment ago. So coming back up here, let me grab this real quick and come down here and paste this in. And I'll just do the first 2 of them because this is a little bit time consuming. So for this one, you stick with these guys right here. So for 0, you multiply by half, you get 0. Then you subtract 5 pi over 12, you'd have negative 5 pi over 12. Then you would take pi over 2 and multiply by a half. So you do that first. And then you're going to subtract away 5 pi over 12. So this is very tedious because you have to get these common denominators. So this becomes pi over 4 minus 5 pi over 12. So we'll say this is, let's multiply this by 3 over 3. So 3 pi over 12 minus 5 pi over 12, which becomes negative 2 pi over 12, which is going to simplify to negative pi over 6. So you see I have negative pi over 6 there. Let's just do one more. I don't think we have to do all of them. You can do them all on your own. This is just to show you that you have different techniques to use. So we have multiply by a half. So let's start with pi. And we multiply by a half. And then we subtract away 5 pi over 12. So this becomes pi over 2 minus 5 pi over 12. Multiply this by 6 over 6. So you have 6 pi over 12 minus 5 pi over 12. So this would give you pi over 12. So pi over 12 there. So again, if you follow this, you get the same result as using the quarter period method. I know a lot of students do not like using graphing transformations for x because the procedure itself is hard to get. And then in this case, it would be a little bit more tedious than what we did with adding quarter periods. So we have our x coordinates. So that's the first thing. Let me put a comma, a comma, a comma, a comma, and a comma. And now we want to find the y coordinates. Now, this is one where you can use graphing transformations very easily. And that's because of the fact that when you plug in negative 5 pi over 12, so if I plug that in there, negative 5 pi over 12 plus 5 pi over 12, well, that's going to be 0. 2 times 0 is 0. So you would get the cosine of 0, which is 1. So notice that this right here, when I go through the process, I get this y coordinate right there. So I could have shortcutted that and not plugged in and just said, okay, well, it's going to be 1/2 times whatever this y value is, which is 1, and then plus 1. Again, if we go back, that's what we came up with here. Multiply by half and then add 1. That's all you're doing. When you look at this one here, again, if you plugged in, and I'll just do it for this one, negative pi over 6, if you plug that in there and you go through the steps, you're going to end up with this guy right here being 0. Because when you plug in a negative pi over 6 and you go through the steps, you're going to end up with the cosine of pi over 2. And let me just show you that real quick, just so that's crystal clear. If you did the cosine of, you have 2 times, let's plug in negative pi over 6, and then plus 5 pi over 12. Okay, so we just need this part right here. I'm going to multiply this by 2 over 2. So this would be negative 2 pi over 12. And what would that give me? Well, negative 2 pi over 12 plus 5 pi over 12, that's 3 pi over 12. And 3 pi over 12, you can say, is pi over 4. Well, 2 times pi over 4, that's going to be pi over 2. So the inside part here, this part right here, is going to be pi over 2, and the cosine of pi over 2 is 0. Well, notice that, again, the y coordinate there is 0. So all I had to do was sit there and say that I know that the result of this will be 0. So I can just say, well, it's going to be 1/2 times 0 plus 1. And then if I was to plug in pi over 12, the result of this part right here would be negative 1. So 1/2 times negative 1 plus 1. Again, so on and so forth. These are just duplicates, so you don't have to do this. So I'm just going to say that this is 1/2 times 1, which is 1/2, plus, let's write 1 is 2 over 2, so this is 3/2. Then this one, anything times 0 is 0, so this is just 1. And then negative 1 times 1/2 is negative 1/2. And then plus, this will be 2 over 2, so this is 1/2. So this would be 3/2, 1, and 1/2. Let me erase this and write those in. So this is 3/2, 1, and 1/2. And again, for this one, it's going to be 1 again. And then for this one, it's going to be 3/2 again. When we think about graphing this guy, let me grab this real quick. I have given you a link for all of these guys that we're going to look at today on Desmos. So just click on that if you want something that has a little bit more detail or is easier for you to follow along with. So you can just pause the video and check these points out. Well, you see that this point right here, again, at the beginning of the cycle, you have negative 5 pi over 12 comma 3/2. Then this right here is a quarter of the way through. You have negative pi over 6 comma 1. So you want to focus on this one right here because this x value is where you're going to have your vertical asymptote. It's always going to be a quarter of the way through. And then you're going to have midway, you have pi over 12 comma 1/2. And then this one right here is 3/4 of the way through. Again, that's where you're going to take this x coordinate of pi over 3. You're going to have a vertical asymptote there. You're 3/4 of the way through. So pi over 3 comma 1, and then you're going to the end of the cycle, so 7 pi over 12 comma 3/2. What a lot of teachers will do is they will draw a horizontal line, which in this case would be y equals 1. They're showing you that the midline of this guy has been shifted up by 1 unit. So this right here would be y is equal to 1. So a lot of students will do that instead of remembering that it's at the quarter and 3/4 and just say, okay, well, anywhere where there's a point that's on that line, well, this has been shifted up like that. So I'll look at the x coordinate. In this case, it's negative pi over 6. It's covered up a little bit. In this case, it's pi over 3. And that's where I'm going to have the vertical asymptotes drawn. So go to the next graph. That's what we have. So here's your x equals negative pi over 6. Here's your x equals pi over 3. That's all you're focused on. This is a quarter of the way through and 3/4 of the way through. That's how you want to draw this in terms of getting the vertical asymptotes for the secant function. Now, once you have that, you're ready to put everything together. So let me just highlight this again. So we have this vertical asymptote and this vertical asymptote. So this is extended to the left and to the right a little bit. But again, if you're doing this on your own, you're going to have this point right here that we found, this point right here that we found, and this point right here that we found. Again, this point right here and this point right here, that's not really relevant anymore because we use it to make the vertical asymptotes, so we don't need that. The idea is that, again, when you see a hill here, it becomes a valley here. So that means that this right here would be drawn to where it approaches that vertical asymptote. And then this right here would be drawn to where it approaches the vertical asymptote. Same thing for this part right here. And again, the way you know that this is going down like that, this right here is going to be a valley, so this right here becomes a hill. This minimum here becomes a local maximum here. This maximum here on the cosine guide is going to become a local minimum here. Then when we look at this part right here, so again, this is a hill, so this would be a valley, so this maximum here on the cosine guide is going to be a local minimum on the secant graph. So this guy right here would be drawn to where it approaches the vertical asymptote and doesn't touch it. All right, let's take a look at another example with secant. So here we have f of x equals the secant of x over 3 minus 2 pi over 3 plus 1. So again, let me just factor this guy so we can get the phase shift more easily. Let me make that a little bit better. So this is the secant of, I'm going to pull out a 1/3, and this one's very straightforward. Let me slide this down so I have room. So inside you'd have x minus 2 pi. Close that down, close this down, then plus 1. Okay, so looking at this, just getting some information, if you want the phase shift, which we're going to use with the quarter period method, you have to undo what's being done to x. So you have this minus 2 pi here. So I'm going to add 2 pi to undo that. So that means I'm going to the right. So I'm going to the right by 2 pi. Then for the vertical shift, again, you have this plus 1 here. So that means I'm going up 1. For the period, again, you're going to take the standard period, which is 2 pi, and you're going to divide by this number outside the parentheses in factored form, or if it's not in factored form, you have that x over 3, so the coefficient of x is 1/3. So it's just 2 pi divided by 1/3, which is 2 pi times 3, which is 6 pi. So your period here is going to be 6 pi, and then the quarter period, that's going to be 6 pi over 4. Let me slide down a little bit. So 6 pi over 4, 6 divided by 2 is 3, and then 4 divided by 2 is 2, so it's 3 pi over 2. Okay, so if you want to do this using graphing transformations, again, typically we always do that for y, but for x, it just depends on the student. I'll just give you the information. If you want to do it that way, that's up to you. So let me put out x and y here. So for x, again, you have to undo what's being done to it, and to do that, you go in the reverse order. So as we talked about in the first problem, this is done first and this is done second because you're reversing the order of operations. You go inside the parentheses first, so now this would be second, and you multiply second, so now this would be first. And you have to undo what's being done. So multiplying by 1/3, to undo that, you need to multiply by 3. So multiply by 3. And then to undo this subtraction of 2 pi, you need to add 2 pi. So add 2 pi. And so what's happening is, this multiplying by 3, that's giving you a horizontal stretch by a factor of 3. And then adding 2 pi, that's going to shift me to the right by 2 pi. Then for y, again, that's very straightforward. You don't have anything outside here. You can just put a 1 if you want. So really, I put 1 and 2, but you just need one thing here. So you wouldn't even consider that because multiplying by 1 is not going to change anything. So really, all you have to do here is just add 1, and so that just shifts me up by 1 unit. So again, if you want to do it this way, it's up to you. I'm going to use the quarter period method because most students find that easier. So let me go ahead and grab this real quick, and I'm just going to erase this and just write in a cosine. Okay, so going back to the basic points we had, so we're going to say that we have 0, 1, again, starting at the maximum. Then you have pi over 2, 0, that's your x-intercept. Then you have pi, -1, so down to the minimum. Then you have 3 pi over 2, 0, so that's your x-intercept. Let me slide down a little bit. And then you'd have 2 pi, 1, so you're at the maximum for the end of the cycle. So we're going to, again, you can use the quarter period method, or you can use the graphing transformations that we wrote on the other page. We're going to find the x-coordinates first. So again, you would start with a shift because this guy right here is 0. So you're just going to add 2 pi because we're shifting 2 pi to the right. So this guy is going to occur at 2 pi now. And then from that point on, you're just going to add quarter periods. So the period was 6 pi, and the quarter period was 3 pi over 2. So if I add that to 2 pi, what that's going to give me, let me multiply this by 2 over 2. So you could say this is 4 pi over 2. So this would give me 7 pi over 2. So this is 7 pi over 2. And then from this point on, you're just going to keep adding 3 pi over 2. So 7 pi over 2 plus 3 pi over 2, that's 10 pi over 2. Again, you could simplify that, but we'll do it in a moment. 10 pi over 2 plus 3 pi over 2, that's 13 pi over 2. And then 13 pi over 2 plus 3 pi over 2, that's 16 pi over 2. So this right here would be 5 pi if you simplified. And then this right here would be 8 pi if you simplified. Okay, so now that we have the x-coordinates, again, for the y-coordinate, you can just use graphing transformations. You could plug in if you want, but again, it's the same thing. So what I would do is I would just say that whatever the y-coordinate is here, I'm just going to add 1 because we're shifting up by 1 unit. So 1 plus 1 is 2. 0 plus 1 is 1. -1 plus 1 is 0. And again, for this one and this one, you can just copy. So for 0, it goes to 1, and then for 1, it goes to 2. And let me paste this in. Once again, I'll just mention this. I have a link for you on Desmos if you want to follow along more closely. Maybe you're having trouble because of the scale of the graph, or you're using a smaller device or something like that. But you see the beginning of the cycle, we have this 2 pi, 2, then we have 7 pi over 2, 1, then we have 5 pi, 0, you have 13 pi over 2, 1, and then 8 pi, 2. The common mistake that students make is they're not paying attention, and they say, okay, I have an x-intercept here, so they draw a vertical asymptote. That's wrong. You want to look at what happens at the quarter, so at the quarter, and 3/4, okay, because this guy has been shifted up by 1 unit. Again, a lot of teachers will take and draw that new midline. So this is y equals 1. Normally it's y equals 0 or the x-axis, but because of the plus 1, it's shifted up by 1 unit. So whenever you have a point that's on that line, you're going to take the x value there, and you're going to say that's where my vertical asymptote is going to be for the secant function. So x equals 7 pi over 2 would be a vertical asymptote. X equals 13 pi over 2 would be a vertical asymptote, so on and so forth. Again, if you want to continue this to the left or the right, that's going to be up to you. Again, you can keep adding quarter periods to your x values to keep going to the right. Remember, the y values are going to cycle. So for the beginning, it's 2. Then for the quarter, it's 1. Halfway, it's 0. Then for the 3/4, it's going to be 1. And then finish up at 2. All right, so continuing, again, at x equals 7 pi over 2, you can have a vertical asymptote. And then at x equals 13 pi over 2, you can have a vertical asymptote. Okay, so coming to the graph, let me just highlight what we just did. So this is your x equals 7 pi over 2. This is your x equals 13 pi over 2. So those are the 2 vertical asymptotes we found for the secant function. And again, all you want to do is you want to take that point, and let's just say it's about right there, and you're going to sketch this to where it approaches the vertical asymptote. When you look at this right here for the cosine, this is a hill, so here it's going to be a valley. So this maximum becomes the local minimum here. And then again, similarly, let's say we make a point about right there, and we would say that you could go this guy approaching the vertical asymptote, and then this way you would approach the vertical asymptote. So just like that. Again, it does not have to be perfect. Just get it as good as you can. Again, this valley right here on the cosine graph becomes a local maximum on the secant graph. Let's say you have this point about right there that you found. So this guy right here would be drawn to approach the vertical asymptote, but not touch it. Again, if you want to extend this to the right or to the left, you can click the link on Desmos and just practice that way. But generally just drawing one cycle of this guy, particularly if you're self-studying, that's good enough. All right, now let's change things up and look at the cosecant function. So with this one, you're going to see that a lot of things we learned with the secant function is just going to carry over. So let's do y equals the cosecant of x. And again, I'm going to do this over one period. Now, negative pi and pi will not be included here because that's going to give you undefined. So let's say that x is strictly greater than negative pi and strictly less than pi. So let's think about this using the unit circle. Let me come back up here for a moment. So remember that the cosecant of x, by definition, is 1 over the sine of x. So a moment ago, I said that it would be undefined at negative pi and pi, but just thinking about where the sine value is 0, so that's right here at 0, right here at pi, so just using the standard unit circle. But again, this is going to repeat every pi. So you have 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, so on and so forth. Or if you wanted to rotate clockwise, you could say, and let me just show you this real quick, if you rotated like this, this would be negative pi. So that is negative pi, that is coterminal with pi. So it's the same sine value. So you could do negative pi, negative 2 pi, negative 3 pi, negative 4 pi, stuff like that. You're still going to get an undefined value for cosecant because the sine value is 0. So going back, you will see that anywhere where the sine value is 0, you're going to get these vertical asymptotes. So again, at negative pi, you're going to get 1. You get 1 at 0, but you typically do not put a dashed line right there because this is the y-axis. So you can put 1 in if you want. Just know that that is a vertical asymptote. So it would be x equals 0, or again, the y-axis. And then here you have pi. But if you keep going, you'd have 2 pi, 3 pi, 4 pi. If you kept going this way, you'd have negative 2 pi, negative 3 pi, negative 4 pi, so on and so forth. So you can basically say this is going to happen at pi n, where n is any integer. When you look at this point right here, so this point right here, you have a y value of 1. So this will be a shared point for cosecant and also for sine. And then here, you have a y value of negative 1. That'll be a shared point for cosecant and for sine. And I'll show you that when we get to the combined graph. So just remember this point right here. This is going to be pi over 2 comma 1. And then this point right here, this is going to be negative pi over 2. Remember, that's coterminal with 3 pi over 2, and then comma negative 1. So again, just thinking about the behavior of this guy, as you go from pi over 2 for that x value, where the sine value is 1, to an x value of pi, where the sine value is 0, well, again, because the cosecant of x, let me write this out, it's because the cosecant of x is equal to 1 over the sine of x, well, the value here, as you go this way and you get closer to an x value of pi, it's getting closer and closer to 0, but it's never going to touch it. So 1 over something that's really, really close to 0, again, this is going to blow up, and we say this increases without bound, or it's approaching positive infinity. Then similarly over here, if you follow this part right here, you're going to decrease without bound or approach negative infinity. So just like we saw with the secant function, same process is happening. It's just happening at different places on the graph. Now, we can go through a few basic points. This is just something you can read through for reference. So if the x value is 0, again, y is undefined. This is also going to happen at plus or minus pi. You would get undefined. Again, this is pi n, where n is an integer because you have a sine value of 0. Then when you think about something like pi over 6, you get 2. Again, just to show you that one, just so this is crystal clear, if you look at this right here, this is pi over 6, well, the sine value is a half. So the cosecant of pi over 6 is 1 over the sine of pi over 6, which equals 1 over 1/2, which again is 2. If you looked at negative pi over 6, I'm rotating clockwise. So we saw that earlier, and so this is coterminal with 11 pi over 6. But the thing is, cosecant and sine, they are negative in quadrant 4. So that means I'm going to get the opposite of this. So I would want negative 2. So the cosecant of negative pi over 6 is equal to 1 over the sine of negative pi over 6, which is equal to 1 over negative 1/2. Again, you can take that y coordinate right there. And so this is equal to negative 2. So that's why these guys are opposites. So coming back down, let's think about, you have pi over 4, that's square root of 2. Then negative pi over 4 would be negative square root of 2. Again, they're opposites. Pi over 3, you have 2 times square root of 3 over 3. Negative pi over 3, you have negative 2 times square root of 3 over 3. Then pi over 2, you get 1. Negative pi over 2, you get negative 1. Then you have 2 pi over 3, you get 2 times square root of 3 over 3. Negative 2 pi over 3, you get negative 2 times square root of 3 over 3. 3 pi over 4, you get square root of 2. Negative 3 pi over 4, you get negative square root of 2. And then 5 pi over 6, you get 2. And negative 5 pi over 6, you get negative 2. So just like we saw with secant and cosine, we're going to use the sine function as a guide when we graph cosecant. Again, where there's a y value of 1, you're going to have a shared point. Where there's a y value of negative 1, you're going to have a shared point. So you're going to use those shared points. Again, when you have a hill here, you're getting a valley here. So this maximum here, again, the range for sine is the same as the range for cosine. It's from -1 to +1 with both being included. So whenever you have a y value of 1, you're at a maximum on your sine graph. So a maximum here gives me a local minimum here. Again, there is no minimum or maximum for the cosecant function or the secant function, but you do have those local minimums and local maximums. Some books call that the relative minimum and the relative maximum if you're used to that terminology. But this hill right here becomes a valley here, or you could say this maximum here becomes a local minimum here. Then this valley right here becomes a hill here. So in other words, this minimum here becomes a local maximum here, and so on and so forth. Then again, the other thing I would call your attention to is that in this form, because there's no vertical shift, when you look at where you have the x-intercepts on your sine graph, that's where you're going to have your vertical asymptotes for the cosecant graph. So something like pi, you would also have 0. Again, we typically do not draw that in for the y-axis. If you want to, it's not wrong, but you would have 0, pi, 2 pi, 3 pi, again, going over here, negative pi, negative 2 pi, negative 3 pi, so on and so forth. So just like we saw with the secant function, the range here is going to be from -infinity to -1, where that's included, and the union with 1 going out to +infinity. So you don't have any y values between -1 and +1. All right, let's spend a little bit of time looking at the characteristics of the cosecant curve. So we have here that the domain consists of all real numbers except pi n, where n is any integer. Again, that's because the sine value would be 0 there, and so your cosecant function would be undefined. We have f of x equals cosecant of x is discontinuous. Again, if there's pi n, where n is any integer, and the graph contains vertical asymptotes at those values. There are no x-intercepts. You're only going to get those when you start shifting the graph up or down. But on the standard y equals cosecant of x, there are no x-intercepts. The period is 2 pi. There are no minimum or maximum values. Of course, we have those local minimums and local maximums that we use to sketch the graph. The range is from -infinity to -1, with this guy being included, and the union with, you have 1 to +infinity, again, where 1 is included, but you don't have any y values between -1 and +1. So keep that in mind. The graph has no amplitude because, again, there are no minimum or maximum values. You're just going to see amplitude when you work with cosine and sine. Now, the graph is symmetric with respect to the origin. So the cosecant of -x is equal to the negative of the cosecant of x for all x in the domain. So f of x equals the cosecant of x is an odd function. So just like the sine function. All right, so now let's talk about graphing variations of the cosecant function. So this is pretty much the same thing as we saw with the secant function directions. So we're going to replace cosecant with sine and sketch the graph using a dashed curve. So that's your guide function. Sine is used as a guide. Sketch the vertical asymptotes. Again, when you think about this, because you have vertical shifts, you cannot just say that the vertical asymptotes will occur wherever the x-intercepts are on the sine graph that you're using as a guide. That will only work if you don't have any vertical shifts. So what I always teach people is they occur at the beginning, middle, and end of the sine cycle. Because remember, on your normal sine graph, you have, let me just come back to this for a moment. So your cycle is going to go from right here to right here. So from 0 to 2 pi. You're going to start out at an x-intercept. You're coming up to the maximum, and then you're coming back down to an x-intercept. So right there. Let me do that in a different color. And actually, let me mark this one, and this one, and this one in a different color, and go back to this one. So let me come down. So you're going down to the minimum, and then you're coming back up to the end of the cycle, which is an x-intercept. So the beginning, the middle, and the end. If you remember that this midline is y equals 0, so you're on the x-axis. If you had something like a vertical shift up by 1, well, then that midline is going to be y equals 1. If it was, let's say, a shift down by 4, well, now it would be y equals -4. So a lot of people will draw that midline in. You can do that. But what I always do is just say, okay, what point am I going to have that's first, third, and fifth? So at the beginning, the middle, and the end, that's where I'm going to take those x values and draw my vertical asymptotes for the cosecant function I'm working with. All right, then I have sketched the graph by drawing the U-shaped branches between consecutive vertical asymptotes. So these guys are going to approach the vertical asymptotes, but not touch them. And we have here the hills and valleys are interchanged. And then optional, I have used the period to find additional cycles to the left or right as needed. If you're self-studying, I recommend just doing one period. You can, of course, just look on Desmos and see it to the left or right as much as you want. But if you're getting this from a teacher as an assignment, they'll generally tell you, well, I want you to sketch it over this interval. So just follow that. All right, let's take a look at an example. So we have f of x equals 1/2 cosecant of x plus pi over 3 and then plus 2. So normally I would factor this so I can get the phase shift. But here, the coefficient on x is 1, so you don't really need to factor anything. You can immediately just get the phase shift. and say that we're going to go left by pi over 3. Again, you've got to undo what's being done to x. You have plus pi over 3, so that means you need to do minus pi over 3. So that tells me I'm going left pi over 3. And then in terms of your vertical shift, you're going to have plus 2 here. So that means I'm going up 2. So if you wanted to graph a horizontal line through the middle of that guy when you're graphing the sine function as a guide, you would sketch y equals 2 for that, because normally it's y equals 0, and this has shifted me up by 2 units. So for the period, it's just the standard 2 pi. So you take 2 pi and you divide by the coefficient of x, and so in this case that's 1, so it's just 2 pi. And then the quarter period, if you're using that method, well, it's just going to be 2 pi over 4, which would be pi over 2. So if you want to use graphing transformations, then let's just put down for x here. You only have one thing you'd have to do. Again, you're just shifting to the left by pi over 3. So you would just subtract away pi over 3. And that's from each x value from your standard points for the, and we're going to work with the sine function in a moment when I swap this out. So for the sine function. And then in terms of the y, you have two things you need to do. Let me put a little border here. The first thing is you multiply by half. You multiply by 1/2. And the second thing is you add 2. So we're going to use this. If you want to use this, that's up to you. In this case, I think it's probably equal time to using the quarter period method, but a lot of people do not like using graphing transformations for x for whatever reason. So thinking about this, this gives me a shift to the left by pi over 3. This right here gives me a vertical compression by a factor of 2, or again, you might say a vertical shrink by a factor of 1/2. Again, I will not get into a debate about that. Just understand that you're either dividing by 2 or you're multiplying by 1/2 for each y coordinate. And then you're going to add 2, that's shifting me up by 2 units. And come down here and paste this in so I have some room. So I'm just going to rewrite f of x equals 1/2 sine of x plus pi over 3, and then plus 2. Okay, let me get rid of this. Move this up. And we just need to get our points. So just start with your standard points for sine. So you have 0, 0, you have pi over 2, 1, then you have pi, 0, you have 3 pi over 2, -1, and then you're going to finish up at 2 pi, 0. So all you have to do is start things off with your phase shift. So that is going to be minus pi over 3. So you take 0, subtract away pi over 3. So that gives me negative pi over 3. Once I've done that, I'm just going to add quarter periods. That's all I need to do. So again, if you're using this method, you're not going to touch any of these x values. You're only going to do that if you're using the graphing transformations method. And I know that gets confusing, but essentially you're just saying, okay, well, the quarter period here is going to be pi over 2. I need a common denominator. So let me multiply this by 2 over 2. Let me multiply this by 3 over 3. So that would give me 3 pi over 6. So 3 pi over 6. And this would be negative 2 pi, so negative 2 pi over 6. You can erase this now. So I'm going to add 3 pi over 6. So that gives me pi over 6. So this is pi over 6. And again, you're just going to keep doing this. So you're just going to keep adding 3 pi over 6. Pi over 6 plus 3 pi over 6, that is 4 pi over 6. Don't simplify yet. 4 pi over 6 plus 3 pi over 6, 7 pi over 6. 7 pi over 6 plus 3 pi over 6, 10 pi over 6. Okay, so now you can simplify. You just want to make sure you're not simplifying, and then you got to get a common denominator again. So 4 pi over 6, 4 divided by 2 is 2, and 6 divided by 2 is 3, so it's 2 pi over 3. And then 10 pi over 6, 10 divided by 2 is 5, and 6 divided by 2 is 3, so that's 5 pi over 3. The other way you could have done this, we only have one thing we're doing to x. We need to subtract away pi over 3. So if you're using that method, you're working off of these values only. So 0 minus pi over 3, negative pi over 3. Pi over 2, let me show you this real quick. So pi over 2 minus pi over 3. Let me make that better here. That's going to give you pi over 6. So if I multiply this by 3 over 3, multiply this by 2 over 2, I would have 3 pi minus 2 pi, and this is over 6. And of course, that is pi over 6. Same thing as I got right there. And you can keep doing this if you want. You could do pi minus pi over 3. Let me just do one more of them, just so this is crystal clear how you can use the different methods. So let's write 3 pi over 3 minus pi over 3. And of course, that gives you 2 pi over 3. So you're getting the same thing. So it's the same result either way. You just have to be completely clear on which method you're using and what steps work with each method. I don't want anybody to get confused. With that being said, let's go through and get our y values. Again, you can always plug in, but you know that if you plug in negative pi over 3 right here, this part right here is going to become this right here. Again, negative pi over 3 plus pi over 3 is 0. The sine of 0 is 0. So this becomes this right here. So the shortcut is, again, just to use graphing transformations, you're just going to say multiply by 1/2 times whatever this is. So that's 0, then plus 2. So then this would be 1/2 times this guy right here, this 1, and then plus 2. so on and so forth. So this right here would be 1/2 times your 0 again, and then plus your 2. And of course, this is a duplicate of this, so you don't have to do this one. We can just erase this one. You could do this one. So 1/2 times -1, and then plus 2. So this would be 2. We know that 1/2 times 0 is 0, and you add 2, so you get 2. So this one's 2, and of course, this one's 2, and of course, this one's 2. For this one, 1/2 times 1 is 1/2, and then plus 2, you could say this is 1/2 plus 4/2, so this is 5/2. So 5/2 is what you're looking for there. Okay, here, this would be 1/2 times -1, that's -1/2, and then plus 2, so let's say plus 4/2, and that would be 3/2, so that would be for that one. So not too bad overall. Again, getting the y values is always much easier. Let me go ahead and grab this real quick. And let me come down here and paste this in. And really, I don't need these. I just need these. So let me move this over so you can see everything. Again, I gave you a link for Desmos if you want to click on that. But essentially, when we graph this sine function as a guide, you have this -pi/3, 2. You have this pi/6, 5/2. You have 2pi/3, 2. You have 7pi/6, 3/2. And then you have 5pi/3, 2. Remember, when you think about this at the beginning, the middle, and the end, again, that's where you have your x-intercepts on that basic sine function. This guy right here has been shifted up by 2 units. Again, this is what a lot of teachers do to make this crystal clear. So this is y equals 2. Again, it was y equals 0, but you have this plus 2 here. That shifted everything up. So anywhere where you're hitting that line, y equals 2, where your y coordinate is 2, so that means that the x value there, that's going to be a place where the cosecant function is undefined, so you'd have a vertical asymptote. In other words, if I plugged in a -pi/3, -pi/3 plus pi/3, that's 0. The sine of 0 is 0. But again, if you had the cosecant of 0, you would get undefined because the sine value is 0. Same thing would happen with 2pi/3, and this is 5pi/3. Hard to see it because it's circled. Let me recircle it here in a smaller way. So the idea is you'd have a vertical asymptote here at x equals -pi/3, and then here at x equals 2pi/3, and then here at x equals 5pi/3. So just showing this to you. So we draw these in as x equals -pi/3, and then you can have x equals 2pi/3, and then x equals 5pi/3. All right, so let's put everything together. Again, here's your vertical asymptote, x equals -pi/3. Here's your x equals 2pi/3, so another vertical asymptote. And then here's your x equals 5pi/3. Of course, you can use your period to get additional vertical asymptotes going to the right or to the left, just depending on how far you want to extend this. But what I'm going to do right now is just concentrate on what we worked on. So we know that we had a point that was, let's just say, about right there, and then one that was about, let's just say, right there. So again, you're going to interchange your hills and your valleys. So this right here is going to be a hill for the sine function, the guide function. So that would mean that it's going to be a valley here. In other words, this maximum point on your sine function here becomes a local minimum on the cosecant function here. And then with this guy, you have a valley on the sine function, so that becomes a hill on the cosecant function. Or another way to say that is you have a minimum on your sine function, and then that's going to turn into a local maximum on your cosecant function. So what we're going to do is draw this to where it approaches the vertical asymptote, but doesn't touch it. So there's that one, and then I'll do that over here as well. And then I'll come down here, same thing. So approaches the vertical asymptote, but doesn't touch it. And then let me do this part right here. So again, that would be good enough for me if I'm self-studying. You've done one period. So if you want to continue this to the left or the right, again, you have that link on Desmos. You can calculate all the things you need, and then you can just use that link to check it. All right, let's take a look at another example here with cosecant. So f of x equals 2, cosecant of x over 2, minus 5pi/6, and then minus 1. So again, I'm going to factor this just to get things started. So f of x equals 2, cosecant of, pull out a 1/2. And so inside you'd have x minus, if I'm pulling out a 1/2, how do I undo multiplication by half? I need to multiply by 2. So this one, you might need to write it out. So 5pi/6 times 2. And so this would cancel with this and give me a 3 down there. So this is 5pi/3. And I know this gets a little bit tricky when you're factoring like that, but you can always check it. A half times x is 1/2 x, or x over 2. Then minus and minus, 1/2 times 5pi/3, that is 5pi/6. So that checks. So then we have minus 1. So at this point, we can just get the phase shift right away. That's why I factor. So for the phase shift, you're going to get, again, how do I undo this minus 5pi/3? I need to add 5pi/3. So I'm going to the right, 5pi/3. This part right here is a vertical shift. I'm going down by 1 unit. So vertical shift. So it's down 1 unit. Then for the period, you look at this 1/2 here. That again is the coefficient of x in unfactored form. In factored form, it's outside the parentheses. But essentially, you take your 2 pi, which is your standard period, and you divide by 1/2. Well, if I divide by 1/2, it's like multiplying by 2. So this gives me 4 pi for the period. If you want the quarter period, because you're using that method, so the quarter period, well, you just take 4 pi, you divide by 4, you get pi. That's all it is. If you want to do graphing transformations, again, it was more simple on the last one. This one, you have 2 things that are happening on the inside. So again, you've got to undo things. And to undo something, you have to go in the reverse order. Essentially, if you look at this, I'm going to go inside of the parentheses first if I'm using the order of operations. I know you can distribute this, but just the way it is, I would go inside of this first, and then I would multiply second. So I've got to undo this in the reverse order. So now this is 1, and this is 2. And I'm undoing things. So for x, how do I undo multiplication by 1/2 or division by 2? Well, I'm going to multiply by 2. So I'm going to multiply by 2. So in other words, I have a horizontal stretch by a factor of 2. Then this guy right here, I need to undo the subtraction of 5 pi over 3. Well, that means I need to add 5 pi over 3. So I'm going to add 5 pi over 3, and that shifted me to the right by 5 pi over 3. Then, again, for the y, this is always much easier and very straightforward. You just follow the order of operations. So you have that 2 that's multiplying this. So we're going to multiply by 2. And that's going to give me a vertical stretch by a factor of 2. And then the second thing is you have this minus 1. So we're going to subtract 1. And then that is just going to shift me down by 1 unit. So if you want to use this, that's fine. You just take those original points for your sine graph, and then you take the x coordinates. You're going to take each one, multiply by 2, and then add 5 pi over 3. That's going to be slower in this case because of getting common denominators. It's going to be faster to use the quarter period method. So I'm just going to stick with that. Maybe I'll show you 1 or 2 points with this just for clarity. So let me go ahead and grab this, and let's paste this in. And of course, what we're going to do is get rid of that cosecant, and we're going to sketch the graph of the guide function. So we're going to put in a sine and make the n better there. All right, so once we look at this, again, you think about your basic points for the sine graph. So you have 0, 0. You have pi over 2, comma, positive 1. You have pi, comma, 0. You have 3 pi over 2, comma, negative 1. And then you're going to have 2 pi, comma, 0. All right, so let me start out by doing the quarter period method. And then once we've done that, I'll do a few points using the graphing transformations. So the quarter period here is going to be pi. Now your phase shift is plus 5 pi over 3. So what you'd want to do is write this with a common denominator. And you could say this is 3 pi over 3. That 3 could be a lot better. And so the first thing here is going to be, I'm just going to shift to the right by 5 pi over 3. So I'm going to say instead of 0, now I have 5 pi over 3. And then to get the additional guys here, you're just going to keep adding quarter periods. So don't worry about these x values here. You're done with that. You just want to add this guy right here to this guy right here, and then just keep going. So 5 pi over 3 plus 3 pi over 3, that is 8 pi over 3. Then 8 pi over 3 plus 3 pi over 3, that is 11 pi over 3. Then 11 pi over 3 plus 3 pi over 3, that is 14 pi over 3. That one could be better. And then 14 pi over 3 plus 3 pi over 3, that is 17 pi over 3. So it's pretty quick in a lot of cases once you get a common denominator. All right, so the next thing is, if you wanted to try this with graphing transformations, again, we were told to multiply by 2 and then add 5 pi over 3. So with this one, you are working with these x values. This one you can just skip because you're multiplying by 0 first, and then you're adding 5 pi over 3. So of course you're going to get 5 pi over 3. But for this one, let's just try it. So pi over 2, you're going to multiply by 2 first, and then add 5 pi over 3. So let's say if we do get 8 pi over 3. So this right here would cancel, and what do you get? You get 3 pi over 3. Plus 5 pi over 3. Let me make this 5 better. And of course, you do get 8 pi over 3. So let me get rid of this. And you can see that works. If you want to do the rest of them that way, that's up to you. All right, so for the other guy, we need our y coordinate. And for that, we're going to use graphing transformations. Again, if you plugged in 5 pi over 3, this part right here would turn into 0. So to shortcut that, all you have to do is say, well, I have this guy 2 right here, times whatever this would be. In this case, it would be 0. And then you have minus 1. And then for this one, it would be 2 times this would be 1, and then minus 1. And this is going to be a repeat, so we just have to do this one. So you would have 2 times, again, this right here would end up being negative 1, and then minus 1. So 2 times 0 is 0, and then you have minus 1, which is just negative 1. So minus 1, 2 times 1 is 2, minus 1 is 1. So you could put that there. And then this one's just going to be a copy, so it's -1. And then 2 times -1 is -2. -2 minus 1 is -3. So this is -3. And then this one you can copy, it's -1. Okay, let me paste this in here real quick. I'm just going to erase this. And so at the beginning of the cycle, you have 5 pi over 3 comma -1. Then at a quarter of the way through, you have 8 pi over 3 comma 1. Then at the middle part, you have 11 pi over 3 comma -1. Then 3/4 of the way, you have 14 pi over 3 comma -3. And then finishing up the cycle, at the end, we have 17 pi over 3 comma -1. So you can get rid of these. Again, where you're looking for where to put your vertical asymptotes, again, at the beginning, the middle, and the end. So just remember that. Beginning, middle, and end. The horizontal line that passes through the middle of this guy is going to be at y equals -1 now because you've shifted down by 1 unit. You have that -1 there. So this is y equals -1 there. A lot of teachers do this to say, hey, if you have a point that hits that midline there, well, you want to take the x value there, and you're going to use that to create a vertical asymptote for your cosecant function. That's all you have to remember. So we'll have one at 5 pi over 3, 11 pi over 3, and then 17 pi over 3. So there's your vertical asymptotes. Again, here's one at 5 pi over 3, here's one at 11 pi over 3, and then here's one at 17 pi over 3. So putting everything together, let's do again the x equals 5 pi over 3, a vertical asymptote. And then the other one that we saw, x equals 11 pi over 3. And then the last one that we found was x equals 17 pi over 3. So we've got those. Again, you can always get ones to the left or to the right, going as far out as you want. And then in this cycle here, we know that we found a point. Let's just say it's about right there. And we had a point. Again, let's just say that one was about right there. So the idea here is that this hill on your sine graph, the guide graph, is going to become a valley on the cosecant graph. Or again, you can always say that this maximum here on the sine graph will turn into a local minimum here on the cosecant graph. Then when we get to this point here, again, this is a valley on the sine graph, so it becomes a hill on the cosecant graph. Or again, another way to say that is that this minimum here on your sine graph is going to become a local maximum on the cosecant graph. So once you have that down, you're just going to sketch this guy again to where this is going to approach the vertical asymptote, but not touch it. And again, just approach the vertical asymptote and not touch it. And then this guy will do the same thing here. So approach the vertical asymptote and not touch it. And then approach the vertical asymptote and not touch it. Once again, I gave you a link on Desmos. If you want to do some additional practice, you can go to the left or to the right by as much as you want and just use Desmos to check your work.